Hello.
Good afternoon.
Good afternoon. Thank you. Shankar, can you hear me?
Yes, I can.
Okay, so you will be chairing this session.
Okay, that's my pleasure. I have an introduction made of Professor Weidemuller, and then I think Sadiq will take it up. Can we check that?
Yes, I think so. You will chair the first session, and then Sadiq will take over.
Okay.
Do you see my screen now, or is it?
Yeah, I can see that.
And do you see a mouse? Do you see a red mouse on it?
No.
Okay,
just
so
just
this mouse.
Yeah.
Okay. All right. So then it's really my fancy Logitech pointer doesn't work with Zoom. I tried it several times, it never worked, so I can give up on that. It's so fancy. It's very sad.
Yeah, so this is how the excellency fails, you know.
Yeah, we failed
really,
miserably.
You know, sad story.
Miserably failed. Okay, so how many participants do you have?
About 80 participants, but not all of them join. So yesterday we had about 40 participants.
And they are eager to ask questions.
Yes, they
Okay.
can ask questions.
Because what I will do is I will stop several times and just give the opportunity to discuss. And I don't care if I get to the end. Yeah. In the worst case, I take the time of Johannes Denschlag.
Sure, go ahead. And you know what? I have some questions for you too. But this will essentially just be about Heidelberg, you know, and the tourist
the castle, Heidelberg
yeah.
Castle.
Yeah, it's broken. I saw that.
The French destroyed.
Yeah.
3 times, and after the 3rd time, nobody wanted to build it up again. It was then I said, okay, it doesn't make sense. They will come again.
Perhaps we could take some of the excellency funding to like, you know, get this going again. Another failure, you know.
So, and the students are from all over the place, or they are from, or they are essentially, where do they come from?
Mostly Indian students from many institutes and universities, and most of them are PhD students.
Okay. Yeah, you had a great program. I saw I would have loved to see some of these talks, but it's impossible at the moment.
You can see these are available in YouTube.
Yeah.
ICTS has one YouTube channel.
Uh-huh.
So if you click on videos, then you can see all the videos.
Okay. So mine is also recorded on YouTube. My talk.
Yes,
oh.
yes.
Then I should not make any stupid jokes. Okay, then
it will be live webcast on YouTube.
Okay, I try to be serious.
Yeah, and there's a big audience there in this YouTube, but the jokes will be greatly welcomed. It will be really nice.
Yeah. Okay. So I try to be serious.
Yeah, if you listen to Martin Zuelin's talk, he kept making like very seriously lot of jokes throughout.
Hi, Sadiq, how are you? Sadiq, do you hear me?
Sadiq, you need to unmute.
Hi, Johannes.
Oh, hi, nice to see you.
How's life?
Yeah, it's a bit trying at the moment in the country, but yeah, things are a bit, yeah, we are pulling along. Could have been worse.
But you at home?
Yeah, I mean, labs are shut and, you know, things have been going in and out. I mean, you know, the lab thing has been not very happy last 1 year. But yeah, that's the way the dice rolls.
So how easy is it for you to get the vaccination?
Oh, okay. So I managed it because actually the problem with vaccination in the country is that there's a lot of vaccine hesitancy. So they first opened it for 60 or 60 plus above, and then they kind of kept pushing down the age limits. And I qualified, and I managed to get double vaccinated, and my wife too. But now they have shut it. I mean, in the sense of they opened the window and then they closed it up again. So it's now the wait has become very long between vaccine shots, actually. So how about in Germany? Germany is now rolling it out quite fast.
Well, we're so slow compared to the States, but you know, we're getting speeding up, I would say.
But Johannes, we are just 6 weeks. I just checked it the other day, 6 weeks behind, lagging behind US. If you look at the numbers.
Yeah, but it was a slow start. But I think it's going fine now. Yeah. So actually, I have my vaccination tomorrow. Yeah. Yeah. But you have to find the right spot to see the doctor. We have these national vaccination spots, and they are always completely booked out. You can't even log on. Yeah, I don't know whether you have, Matthias, whether you have some experience with this, or you just went privately.
My wife is a medical doctor.
Yeah, so. Yeah, no question then.
That makes the things but she's vaccinating like hell. Yeah, there's no dose being not given. I mean, friends of hers, they had 2 doses left in the evening. They went to the pharmacy down below and they asked who wants the vaccination. So everything is pushed out at the moment. Yeah, every dose is being vaccinated. They always find an arm.
Yeah, yeah, I would volunteer too. You know.
So maybe it's time to start now, Sourav. What do you say?
Yeah. Please go ahead, I think.
So our chairperson is Professor Shankar De from Saha Institute of Nuclear Physics, Kolkata. So please over to Shankar.
Okay. Yeah, good. I would say good afternoon or good noon, and welcome everyone to this session. And I'm asked to actually introduce Professor Weidemuller, and I gathered some points from his CV in the website. So yeah, if you allow me, then I can just say them. So he started his education in University of Bonn and in University of Munich. And then he did his diploma in 1990 and his PhD in physics in Ludwig Maximilian University in Munich in 1995. But within that short period of time, he had actually worked with Nobel laureates in Professor Theodor Hans in MPQ Garching and Professor Harosh in Paris. And in his postdoc as a Marie Curie postdoctoral fellow, he worked in the University of Amsterdam and FM Institute of Atomic and Molecular Physics, and also in Max Planck Institute of Nuclear Physics in Heidelberg with Professor Rudolf Grimm. In 2000, he started his habilitation in physics in Ruprecht Karl University in Heidelberg and became the research group leader of laser cooling group in Heidelberg. And in his illustrious career, he had been the guest professor in the University of Innsbruck and also in Optics and Photonics Center in University of Sao Paulo. And very interestingly, he had been a Quinn Ren Jihua, that's 1000 Talent Plan chair professor as a part-time in the Hefei National Institute for Physical Sciences at the Microscale and University of Science and Technology in China. And at present, he is the full professor for experimental physics and vice rector in innovation and transfer in Ruprecht Karl University, Heidelberg. He's a fellow of American Physical Society, and he had been the founder director of Heidelberg Center for Quantum Dynamics. So that's really a long CV, I guess. And Professor Weidemuller works on various research subjects such as mixtures of ultra-cold atoms and molecules, strongly correlated Rydberg quantum gases, hybrid ion atom trap for cold chemistry experiments, and Rydberg physics with ultra cold 2-electron systems. And while actually going through his website, I was really happy to see that as being a physicist, we like to do something for our society and in our own ways. So his group participated to the Physics Institute's effort to create an emergency ventilator to support patients suffering from COVID-19, which they call it as HD vent, emergency ventilator systems. So that's probably the need of the time. So over to you, Professor Weidemuller. The mic is yours.
Thank you very much. Thank you for this very kind introduction. And thank you also for mentioning this activity. What I think is great about this activity, first of all, it was started by a young researcher who had actually a quantum physicist, and it was done by quantum physicists, and it was done by joint work with the medical center, but also with our workshops. So everybody spent time voluntarily to do that. And we made it now public. You can download it from the archive. You can build a ventilator for $500. You can find all the material at GitHub. I mean, hopefully it's not being needed much, but that's where we thought also we should do something. Exactly what you said. And I was so amazed in particular by the young people, how much enthusiasm and work they spend on that. Yeah, it's great to be here. Actually, usually I would like to be there in person in India. That would be much more of a pleasure, but we should take it as it is. And we should be happy that at least we can run these events in this way. And let me share my screen. What I'm going to talk about today is our work on using highly excited Rydberg atoms as a platform for quantum simulation. I guess that Tilman Fau was probably already giving some very nice introduction into this entire field and his own research. So I'm at the Heidelberg University. Heidelberg is a touristic place, as you can see here. On this, there's this famous Heidelberg Castle, many times destroyed, always by the French, unfortunately. The third time it was destroyed, they never built it up again. And now it's one of the most famous ruins in Germany. It's a very picturesque town, but it also has this university. Just to give you an idea where we are or where I am currently physically here, this is in the center of Europe, if you plot it the right way. What I like particularly is you can see France is very close. Here is Paris. So there's still an exponential decay of good food into Germany here from France. And it's a very nice place because it's somehow you can get everywhere pretty fast. Frankfurt Airport is just less than an hour away. Touristic town, Berlin, Paris. So Paris is closer than Berlin, which I personally also enjoy because it just takes 3.5 hours by train to go to Paris. It has the oldest German university since 1386. It was founded. It's one of Germany's excellence universities, and it's what we call a comprehensive university. There's all disciplines that you can have at a modern university are present at Heidelberg University. Actually, we just founded, or we're going in the process of founding also now a School of Engineering. So that is filling the last, let's say, the last gap that we have. It also has a very famous history in terms of Nobel Prize winners and laureates that went through this university. Some names that you might know: Ted Hensch was doing his PhD here. Wolfgang Ketterle worked here for several years, actually in the institute just here behind my window. In the rankings, Heidelberg is also scoring quite well internationally. In the physics department, actually, we also cover all topics. This is here, the different topics covered by the physics department. I guess the only topic that you can't study or that you cannot do research at Heidelberg University physics department is plasma physics, but all the rest, there is specialists and institutes and research going on. It's the largest institute in Germany in terms of physics. So it covers all these different scales, from the small, the big, and what we love particularly, of course, is the complex, using our modern atomic molecular optical systems. Okay, so as you already mentioned, in my group, there's several activities. One is on using mixtures of bosons and fermions. I guess Martin has also showed his beautiful work on creating polarons in these systems and studying effects. There is an activity on ion-atom interactions, which I know also some people here in the audience are very interested in, and you are going to hear also the talk of Johannes Denschlag afterwards that is dealing with this. We are using negatively charged ions, OH minus plus rubidium, and had recently some very interesting results there. But what I would like to discuss in detail today is our work on using Rydberg atoms for quantum simulation. So that is an effort being done here in Heidelberg. And as you mentioned, I'm also running a group in China where we are studying also Rydberg physics, in this case, not using single electron systems as in Heidelberg rubidium, but using 2 electron systems, strontium. Okay, so what I'm going to address here as a topic or as a guiding theme is magnetism. So magnetism is, of course, something that we all know from our daily experience, more or less. We all know these magnets, and you can buy these nice toys. Here, this one I like particularly. It's called Smart Max because my youngest son is called Max. And this is also, of course, present. We have the Earth's magnetic field. So it's one of the most, let's say, most miraculous things that we have is this magnetic force and the source of magnetism when it comes to having certain materials that show ferromagnetism. And people already thought for a long time how you might trace these effects back to microscopic origins. The first approach with the advent of atomic physics was the Lorentz atom, where you just consider that you have a charge here that rotates around a positively charged nucleus. It rotates around, and therefore this current creates a magnetic dipole moment, and this magnetic dipole moment then creates a magnetic field. And now this dipole moment can interact, these dipole moments can interact with each other, or they can interact with external fields. But already in the, I guess, 20s, it was clear that this kind of source or origin is not sufficient to explain macroscopic magnetization in materials, because there was this Bohr-van Leeuwen theorem that says that in a classical system, there is no magnetization if it comes to thermal equilibrium. The help came then by the discovery of the electron spin. As you all know, there is an intrinsic magnetic moment associated with each fundamental particle, the electron, and this magnetic moment is directly associated to its angular momentum in the spin. This magnetic moment is just proportional to it. We have the G factor here, which is about 2 for the electron. And now the approaches that are being pursued to understand magnetism on a macroscopic level is to say we have all these elementary spins in the system, and they now interact with each other, and there is now emergent phenomena occurring once we let them all interact. And the description in terms of the fundamental microscopic Hamiltonian is seemingly very simple. You just write down now a Hamiltonian which consists of the different magnetic moments of each particle proportional to their spin. So this is here Si, Sj. And there is now a coupling constant that determines or that describes the interaction of this spin with that one, this spin with this one, that spin with this one, and so forth and so forth. So you sum it up, and it seems that this is a super simple Hamiltonian. You just solve it, and what you get is magnetism. But we all know that it's not as simple as that, because the origin or the deeper nature of magnetism is about the correlations that now are emerging from this kind of interaction, and that are not easy to describe, because we all know that it's hard to solve the Schrödinger equation for many body Hamiltonians. And you probably heard many talks already in this school concerning this kind of phenomenon. So there's these correlations, and in the quantum realm also entanglement that is being built up through the action, through the existence of these interactions, and described by this seemingly simple Hamiltonian. So from my perspective, it's getting even more interesting, but that's of course a matter of taste. You can use ordered systems, but I love disordered systems where you have an additional feature, and that is that these spins are not even orderly assembled here in space. And then the question is, how does then any kind of magnetism emerge, and how does it develop in time? Because you have this competition all the time between ferromagnetic and antiferromagnetic interactions, depending on which directions you look. You have these effects of frustration. The question is, how does this entanglement build up, and how does that later then lead to a specific magnetization and the dynamics of this magnetization? And all is governed by this very simple Hamiltonian. We call this Heisenberg models because it was first studied by Heisenberg. And in the case of disordered systems, there had been many, many investigations in the past. Here, this is from some papers that are already 30 years old, where people saw that in these disordered systems made up out of spin glasses, as they are called, there's a very interesting dynamics of the magnetization. The magnetization seems to decay or relax very, very slowly, as you can see here on these scales here. It's almost logarithmic, this decay of the magnetization. So the system is never in equilibrium. There's always some dynamics going on, and this dynamics is very, 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 very slow. It happens on very, very long time scales and follows certain kind of, as we will see later, follows certain kind of characteristic functions. So the question is, what is actually driving this? So the first question, and that is a very fundamental question, and I'm not sure, but maybe some of the speakers here also in your conference and school have already addressed that, is if you take an isolated system, how at all does such an isolated system actually reach its equilibrium? And then the question is, the dynamics, if you follow it, how do correlations, and now be it classical or quantum correlations, how do they influence the dynamics of the system? And how does this dynamics actually depend on the degree of disorder, the nature of the interactions, so being dipolar or other interactions, and the symmetries of the system? And that is the questions that we are trying to address with our system. And you probably know that this is, of course, one of the, let's say, paradigms of using quantum computers or quantum simulators. And of course, you probably have seen and known Feynman's original citation on the definition of a quantum simulator or quantum computer. Here I'm using one of more recently. Caden Hazard wrote this in a nice article here in Physics describing another experiment. But what I find funny about this description here, he said, to describe what a quantum simulator is, I first will have to disclose a fact that is particularly painful for us theoretical physicists. So I hope there's no theoretical physicists here in the room. We can rarely predict the behavior of quantum systems with more than a few particles. And this is not a consequence of limited mathematical prowess or computing power, but the fundamental difficulty of solving quantum mechanics with classical machines. So if you want, this is a reiteration of Feynman's theme. And what I find interesting in particular when being said by theorists is that the theorists are now calling for controllable quantum systems by the experimentalists. So that is, of course, this essential idea. We need to build controllable quantum systems that allow us to model certain Hamiltonians. And that is what this entire quantum simulation game is about. So what I would like to do is introduce you then on a specific platform, and that is Rydberg atoms and their specific application to spin models. I'm going to show you then two interesting recent examples of what we found. We found some surprising dynamics, universal glassy dynamics in these systems, and I'm going to show to you then some very, very recent approach where we use Floquet spin Hamiltonian engineering that allows us to now, starting from a naturally given Hamiltonian, change this Hamiltonian and break symmetry after symmetry in the same system without changing anything but changing the Hamiltonian through Floquet engineering. All right, so I can be rather brief, I guess, on this introduction on Rydberg atoms, because there had been classes already, courses here, which I'm sure covered this in great detail. It's highly excited atoms, and what we like is that if it goes to highly excited electronic states, everything looks like hydrogen. If I'm just highly enough excited, the states are, the energy of these states is given by this Rydberg formula here, that the energy is just inversely proportional to the square of this principal quantum number. There is a small additional correction, that is the quantum defect, and the quantum defect gets smaller and smaller the larger the angular momentum is, just because the electron at higher angular momenta is no longer entering the inner core, and therefore it really looks like hydrogen than the atom. So in this sense, from an atomic physics point of view, this is pretty simple objects. They are already historically very, very important. This is here from a paper of 1879, I guess. Most of you weren't born then. So this is where people studied spectroscopic series, and already there they realized, and that was a really fundamental and amazing discovery, they realized that these spectral lines, they follow certain specific rules. And it was finally Rydberg in 1890 who figured that all these different energies could be described by this very simple formula that we still call the Rydberg formula. But you have to imagine at that time, there was this vast plethora of different spectral lines. They didn't seem to be connected to each other, but now plotting them in the right way, and that's what Rydberg did, you could find these series, which are then called SPDF. We now know that they are associated with the angular momentum of the electrons, but at that time, these letters stemmed from a heuristic characterization of these lines. So there was the principal line, the sharp ones, the S states, which are hardly influenced by electric fields, the diffuse ones, and the fundamental ones. That's where these letters S, P, D, F, and so forth come from originally. So the amazing discovery of Rydberg was that there is this universal constant that is independent of the specific particle that I use, and therefore what he found then is that this constant is something that has to be explained by something deeper in nature. And we know that later Bohr, and I think that was one of the first big victories of quantum mechanics, Bohr figured that just from a simple atomic model, you could track back this constant to some more fundamental constants like the electron charge, the electron mass, and of course Planck's constant that enters here. So that was one of the very early and very important victories to make quantum mechanics become a success. This universal constant could be described by the fundamental constants. So these Rydberg states, they are really interesting beasts. Yeah, this is here wave functions. You can see that these wave functions, for example, for n equals 100, they go out to 20,000 Bohr radii. This is huge objects, and they are quasi-classical because the distribution of this probability follows very closely the classical motion of a charged particle around a certain charged nucleus. So they are quasi-classical. They are huge. As I said, this is the 30s state. This would be here a DNA molecule. I took this from a course of Serge Roche. This is here the size of a tobacco mosaic virus. So they are as large as viruses or even larger. The world record here, this is from a paper of 2012, is creating Rydberg states of n equals 620 micron size. And the orbital period is also very slow as compared to a ground state atom, 30 nanoseconds. So this is things that you can easily track and measure with rather simple technology. It's very difficult to produce them, but once you have them, they are very nicely behaved. So there's important scalings. Of course, there's the scaling with the principal quantum number, the binding energy. The orbital radius goes with the square of the orbit of the principal quantum number. That's why these beasts become so large. But what is most important for us is that the polarizability is actually scaling as the 7th power of the principal quantum number. So they are very polarizable. The electrons are very far apart, and therefore they are very susceptible to electric external fields. And that leads to very huge interactions, van der Waals interactions, dipolar interactions. If you do the math, they scale as n to the 11th power, and that leads to very strong interactions of the order of, and here this is given in hertz, the interactions as a function of distance, of the order of kilohertz or even megahertz, or even larger, depending on how you choose the distance, at distances that are macroscopic. So you can have two of these atoms at macroscopic distances, and yet they interact with huge forces and huge interaction strengths. The only system that shows larger interactions, of course, are the Coulomb systems, so the ionized systems. Okay, so there are certain effects that are related, and you have heard about this in this school. Here there is this dipole blockade, which makes it impossible to excite two atoms if they are too close to each other. So what you usually have, you excite these atoms from the ground state, and there's a certain distance to within you will never find a second excitation in your gas. So that's a very important concept. It was originally proposed by this group here of people to form quantum computers or quantums, but it later turns out also to be a great tool to study many-body physics with these Rydberg atoms. And this field, I mean, and you have seen already many examples. Vladan gave a talk, Tillman gave a talk, and I may probably others. We have seen many different applications. You have seen a few body physics, quantum optics. I'm sure Vladan was talking about that. Energy transport is an important topic, but what I will concentrate on now is the applications to quantum simulation. So what kind of quantum simulation we have in mind here? So what we want to do is we want to use these systems as a spin system. And there's different possibilities how you can do that. Either all the atoms are in the ground state, and then you excite them to a Rydberg state, and then this quasi, or this two-level system forms a quasi-spin consisting out of the ground state and the excited state. And if you look at it, then these excited states, they interact via the 1/R6 interaction, and you end up with an Ising model for these systems. And this kind of Ising model character has been studied by many groups. Here I show one important example by Antoine Broy's group, where they show that now placing these atoms on this kind of racetrack, for example, using optical tweezers, you can now study Ising models and their correlation functions. So typical quantum simulation applications that you can now do using the ground state, Rydberg state, manifold as a effective spin system. There's also work by Michael Luki, Markus Greiner, Vladan Vuletic, Immanuel Bloch, Christian Groß. Many different groups are studying this kind of system. Actually, we also studied this some years ago together with Kenji Omori in Japan with his group. So that is one application of spin systems using now the Ising model. Another thing that you could do is, instead of using the ground state as part of the system, you're using two Rydberg states. Now you use a ground state here, you use a Rydberg state with a certain character, S character, and another Rydberg state with P character, and you couple them by a microwave. And that system then actually represents a dipolar XY Hamiltonian. Or you can even go to another situation where you use two Rydberg states of the same parity here with the same angular momentum as down and up spin states. You can also easily couple them by two photon transitions, which are having large cross sections in the microwave regime. And then you have XXZ Hamiltonians. So already by choosing the right subsystem, you can choose certain spin Hamiltonians. And you can then get the entire Heisenberg Hamiltonian by also applying additional fields or by applying the tunings of your coupling. So that is a realization of different Heisenberg models that you can do by just choosing the right states. And what we were interested in is then studying this quantum magnetism using exactly this interaction Hamiltonians that I introduced earlier when I talked about this magnetism and this slow decay of these spin glasses. So this is how these experiments look like. We trap the atoms in a dipole trap, optical dipole trap. Then we excite them by some lasers into these Rydberg states, and then we can field ionize them to detect their internal state, so the Rydberg state, and also to detect the numbers of Rydberg atoms that we actually excited. So let me now first show you a first observation that we made that is actually still not fully understood, but it was for us a pretty, let's say, surprising observation, and that is the observation of glassy dynamics in this system. So how does the system look like? So we start with this gas of ground state atoms. This is trapped in an optical dipole trap, so it has this characteristic shape. So and you can now consider on all time scales that we are interested in, and that is timescales of microseconds, you can consider these atoms to be totally frozen. So we don't care at this level, we don't care about the motion of the atoms. So they are fixed in position in space. Then we excite them to a Rydberg state by optical transitions. So now we have the system being here in one of the two Rydberg states that we are interested in. In this case, the 48S state, that's our lower state of our spin system. And one important thing to already consider here is this excitation, this optical excitation process. It's also now influenced by the dipole blockade. So our initial spins, they have a minimum distance. So there is no two spins beyond or below, I should say, below a certain minimal distance. In this case, it's a few micrometers, maybe 5 micrometers. And then we prepare the sample of, I don't know, 1,000 spins or so. All are in the down state, and this is an isolated system. It has no entropy. Another advantage of using these strong couplings and fast timescales is we don't need to worry about single particle decoherence, because we are talking about microsecond timescales. So noise and other thing on the external devices that we have doesn't play a role, at least not on the timescales and the level that we are interested in. Okay, so the next thing we do is we just now do spin manipulation. Global spin manipulation. We shine in the microwave pulse and we put all the spins, we put all the spins along the X direction in this language. So a superposition of the ground and the excited state, or the two spin states, the up and the down state, I should say. And in this case, the system is now described by a magnetization that points towards the X direction. Then we let it evolve under the action of this Hamiltonian. In this case, it's an XXZ Hamiltonian. And we do some tomographic readout like everybody does working with spin systems. And as we can do that with a microwave to map out the magnetization after the system has emerged. So that is what we do, and what you would expect now for this specific initial state. And that is what I show here in this, that is shown here in this graph here, is that the spins are all in the X direction. And since this is now an eigenstate of this Hamiltonian, in the mean field picture, you would not expect that the system has dynamics at all. Because in the mean field picture, these two terms vanish, and we have excited the system along the X direction. Therefore, we don't expect any dynamics to happen. So the system should just precess by its own mean field, because all the spins are pointing in the same direction, should just precess here slowly and staying in this direction along the X direction. Okay, and that's what you see here in this little video here. You can see the dynamics is, if you want, is frozen. It's the system creates its own field. The spins are locked because of the in this mean field picture. So that's what you would expect from a mean field. So this is here now measuring the spin, and you would expect from a mean field approach, you would expect that the spin stays constant. But what we observe is that this system is actually undergoing some relaxation dynamics. So that is the first interesting observation. You observe something that doesn't correspond to any kind of mean field prediction. There's a big qualitative difference to a mean field prediction. And that's of course what you always hope for when you do quantum simulation. You hope that you find something that even qualitatively cannot be explained by simple, let's say, quantum mechanical models. So that is the measurement. And what actually happens, and this is something we know by solving the problem on a finite number of particles, maybe 10 or 12. So what happens actually, all spins are pointing in one direction, but now through this interaction and the action of this Hamiltonian, what it happens is there's a buildup of correlations, entanglement in the system. The spins are getting here entangled, they merge to, or they develop into spins that are no longer having a precisely defined direction, and therefore the system slowly relaxes in its total magnetization through this buildup of entanglement, relaxes to a zero macroscopic magnetization state. So there's another way how we can try to approximate this problem using theoretical methods. One is the so-called discrete truncated Wigner approximation. That's where you start with the initial quantum distribution, mapping this on a Wigner distribution, and then you let this evolve classically. So that is an approximation, as you can immediately understand, because you use the initial quantum fluctuations. They are still in the system, but the subsequent dynamics is classical. Therefore, you don't capture the full buildup of of correlations and entanglement in the system through this approximation. So this is actually here in this paper by Jonas Schachenmeier, Anna Mayer, and Pikowski. And in fact, it describes this, this kind of truncated Wigner approximation describes these data quite well, I would say. So this is here, this curve here, and you see that also in this model, this relaxation is captured properly. And it's also captured that in the y direction and in the other directions, we don't see any dynamics. So now going one step further, it turned out that also, let's say, just heuristically or empirically, we can describe this system by something that we took from spin glass physics, and that is what is called a stretched exponential function. So we just fitted these data with a function that looks like an exponential, but it has this additional stretched exponent here, beta. If beta goes to 0, then you can expand this, and you find that this, if beta goes to 0, you have a logarithmic behavior of the decay. If beta is 1, you have a simple exponential decay. As it turns out, in our case, this beta is 0.4. So it's non-exponential. It's also non-logarithmic. And that is exactly what people found for these classical spin glasses. So although we have an isolated system, interestingly enough, what we find is that this system undergoes also glassy dynamics. So we looked into this a little bit more in detail, and what we found was that now just taking this Hamiltonian here and seeing that this coupling constant here in this disordered system scales as 1 over r to the 6, is that we could just do a simple rescaling of our time. So the rescaling of the time would be just to take here the time divided by this characteristic coupling and the length scale to the 6th, where the length scale is given by the, if you want, the Debye radius, so that is something like the mean distance between the atoms. So this is a characteristic time scale of the system due to this characteristic coupling constant that we have here and the action of a dipolar van der Waals interaction. And if we do so, then we can plot now our data, same data as you saw before. We can plot them on this new let's say new scale time. That is the x. That is now the x magnetization, and that is now the surprise that I show here, and that is what actually we didn't expect. All different measurements that we did at all different initial densities, they all fall into the same graph. So one thing you could say, okay, fine, that is because you did this rescaling. But at the same time, one also has to consider that for all these different realizations, the blockade plays a different role because we changed the density to change this scaling. And that means also that the blockade plays a different role. Here we have a sample here for lower densities where the blockade doesn't matter. The system is very sparse, very weakly populated. So in this case, there is no initial correlations in the distances between the particles. But if we go to higher and higher densities, the system becomes more and more ordered in the sense that the typical extension of each particle or the extension of each excitation or the next nearer neighbor distribution becomes more and more peaked. And yet, despite this change in order, if you want, all data fall onto the same universal curve. So we can also look at this in a different way by just looking at the probability density of our coupling constants here. And you can see that there is this blockade cutoff, and this cutoff doesn't play a role if we go from if we stay at very low densities, because it doesn't matter much if the system is now blockaded or not. But this cutoff plays an important role in this distribution of the J's if we go to the higher density samples. And again, I mean, this red curve and this distribution function, although they differ significantly, all the data fall onto the same universal graph, and they obey the same universal, let's say, if you want, stretch exponent, 0.4. In fact, this kind of behavior is also qualitatively captured by the simulations that we did. So this is here now the results of the simulations. And you can see that for high density samples, you still see some remnants oscillations due to the ordering and due to the, let's say, revival of certain exchange interactions. But if you go to higher and higher densities, also the simulations show that the system somehow goes to this kind of regime where everything seems to be following some universal character. So in the strongly disordered system, there is this universal relaxation or this stretched exponent 0.4. We can do this simple rescaling and we find also a universal amplitude, whereas in weakly disordered systems, the system is still depending on microscopic parameters. So that is the major finding of these experiments, which is also shown here, that for small enough a typical distance here, this beta stays constant, and it only deviates from this constant here if we go to a weaker and weaker disorder, more and more order. So what we would like to do, and what we partially did already, is we want to now look in more detail into this dynamics. What we recently measured is we mapped out what happens if we additionally apply a external field, and we find some characteristic interesting behavior in the susceptibility or in the response to an external field here, with a peak structure that never goes beyond 0. So if you have an external field and you reverse the external field suddenly, but the system stays in its own magnetism, it's hard to see. The system stays in its own magnetization all the time, and it never becomes negative. It never follows the field to a negative value. And we are also studying now the dynamics across boundaries. Actually, this is something we are doing currently in collaboration with Antoine Bois in Paris. Okay, let me look at the time. Maybe what I should already do is allow for some questions after this first part. Maybe I just stop sharing, because I will come to a second part and would like to first maybe take some questions at this point. So maybe I stop the presentation and ask if there's now questions to this relaxation, aging, glassy dynamics part.
Yeah, hi, this is Sadik. Can I ask you a question?
Sure. Yes.
Right. So the thing is that this relaxation dynamics is kind of pretty exceptional, and spin glasses has been around for extremely long time. Sorry, my video is cutting. I mean, this is a persistent problem. What I want to ask you is that from this kind of an experiment, what do we actually hope to get for the condensed matter system? I mean, how does this class of experimentation, which is very important because you're going into a regime which is not, a very controlled regime. So you're allowing the system to evolve into situations which are not tailored. So what is the insight we can feed back into the condensed matter system?
Yeah, that's a very interesting, question. So there are several aspects. First of all, this is the first time this kind of glassy dynamics is observed in an isolated system. All the other systems, like the spin glasses, the typical situation that you have is that they're spins, but they're embedded in some kind of thermal reservoir. So there's still a description in terms of, for example, you can get these stretched exponentials as sum over usual exponentials. And one of the pictures that you might have on these processes, if you have a thermal reservoir, is that each spin sees a local differently environment. So each spin has a little bit of a different decay rate. And therefore, if you add all this up, you get to the stretched exponential behavior finally. So that would be the situation or the description. That is one of the descriptions that are there for certain models, which lead also to this stretched exponent decays. But here we have an isolated system. So somehow, and that is exactly what we are currently addressing with these new experiments where we change the external field, somehow this is linked to questions like the eigenstate thermalization hypothesis, or questions like, does each, even in an isolated system, is it a good description to see each spin being embedded into something like a local environment? But now in this case, this local environment is created in a fully coherent fashion in this isolated system. Yeah. So that is the things that we try to figure out in this case is what is the connections to the eigenstate thermalization hypothesis. A second important question, maybe just to continue put this point, is this is a system out of equilibrium. Of course, I mean, the system never reaches equilibrium, takes forever. to which extent dissipation fluctuation theorems can still be applied here, and is there maybe extensions of the equilibrium fluctuation dissipation theorem that might be applied to such systems that are isolated. So in this sense, I would say it's addressing non-equilibrium dynamics and the question of how do isolated systems reach their equilibrium at its best. And we, of course, we hope to find any kind of, let's say, universal, or universal is a big word, any kind of descriptions that capture these features in a system independent way.
Yeah, thanks.
Okay.
Thanks.
Saikat has a couple of questions. Can Saikat unmute and ask it?
Yeah, I think both questions are the same. Firstly, like, do you see any independent effects? And because you mentioned ETH, like whether ETH is valid here because of the finite size, basically.
Yeah, that is, that is again a very important point. I mean, we are dealing here with 1,000 particles. It's large compared to typically what you can do in these small arrangements, but it's also small. It's still small. It's larger than, let's say, 10 particles, but it's smaller than a million. So we probably will see finite size effects. That is something we actually have to study, in particular when it comes to this ETH. And there's another thing we never reach. How to say? We are always bound to certain finite times. So we can only study the system over a certain range of times. So that's why your conjecture or your remark is very important. I think it will be hard to make, like for every system, it will be hard to make strong claims about the ETH at the end. But I think from what we see also already right now, one can at least get some hints on whether this is related to ETH, and ETH holds at least in this transient, I would call it at least in this transient regime, and as you also rightly mentioned, at least for a system that is somehow maybe mesoscopic, I would say, yeah. But as you, the failure, or one of the reasons, the methods that we are currently applying, they fail in two ways. Either we use a finite 12 particle system, then we are totally bound by the simulation of 12 particles, because as you say, we immediately go to a situation where the correlations are emerging over a larger range than the size of the system in the simulation. Or we use this truncated Wigner, but then we miss the buildup of entanglement in the forthcoming dynamics. In our system with 1,000 particles, it's still, it still might be possible that the size is still too small to see the long-term behavior and to capture all the features of the long-term behavior and the fluctuations, the very small fluctuations and the very low energetic excitations of the system, that our system might still be too small. So in this case, I think we would only make claims for any kind of transient finite size system.
But do you see any can you change the particle number? Do you have a control on that? Do you see any independent scaling?
Not on the level, no, we don't see. Not on, I mean, you saw that there is still error bars, there's fluctuations. On this level, we don't see effects. But one of the things that's going to be interesting, now we're doing this experiment with Antoine, which is in an extremely other regime, 10 particles, maybe 15. And then we will see if there is.
So your Hamiltonian has a summation, right? Like, so there's like, there should be n scaling with.
Yeah, sure. But it's there's trivial and non-trivial finite size effects here.
Yeah, we have another question from Vinamra that's related to Sadiq's interaction. That is, can we think of a thermal passage around interacting spins, taking the condensed matter thought string further? Yeah, I mean,
my picture also tends to be that somehow, although the system is isolated, there might be a way to maybe consider each individual spin to be embedded in some kind of emergent bath. Yeah, but this has to be worked out. I mean, I can tell we have a paper on the archive where for the Ising model, which is not the ones that we are describing here, for the Ising models, we actually found that that there is we find an even analytical solution for this, And maybe starting from that, one might think of these, these thoughts, one might spin them further, but this hasn't been done yet.
Yeah, okay. I guess.
Can I just ask something? So if you remove all the atoms and you just allow the Rydbergs to be present, how do you expect the dynamic to change actually?
Can you say again? So you would,
if you remove the atomic, the unexcited atoms, and you only keep the Rydbergs in, I suppose this is something that Anton Brouwer can do.
We also can do this. The ground state atoms, they don't matter for what we are doing here.
Yeah, but are we completely sure about this? That the ground state atoms are just spectators and they do not play at all any role?
Totally. Because the interactions are a million times weaker.
No, because of the environmental aspects, you know, you are blockading.
Yeah, but they're like vacuum.
Okay, fine, thanks.
This is really a million. It's so large scales. Yeah, the ground state atom in this case. I mean, I know, but it's in this case the interactions we are talking about tens of megahertz interactions.
Yeah.
At densities of 10 to the 11 particles.
Right. Yeah. Okay. Fine. Thanks.
So there's no way that the ground state atoms might make trouble in other ways, but not in this way.
Okay. Thank you.
Yeah, there are no more questions in the chat box.
Okay, no more. Okay, great. Because I see that we are running out of time. I will be brief on the last part. Although I'm, of course, like always, the things that you did the latest are the ones that you're most excited about. This is this Floquet Hamiltonian engineering. Let me just rush a little bit through it and give you the major thoughts and the major ideas. So it would be great if we could take a system which is governed by some kind of natural Hamiltonian, and by just driving it dynamically, we could go to a system that is governed by a different Hamiltonian. And that goes under the name of Floquet Hamiltonian engineering. So you can then go from a time periodic Hamiltonian, this is time periodic, to an effective description that is then averaging over one cycle, and then effectively the dynamics is governed by this efficient, effective Floquet Hamiltonian. And this has been used, I mean, it started with the decoupling of spins in the early spin echo ideas here by Hahn in 1950. So 70 years ago. But it has also been applied now in more and more systems of atoms or trapped ions or NV centers to change the structure of Hamiltonians. So either by studying non-equilibrium physics, sensing, or band structure engineering in optical lattices. So what we use is a discrete.
Matthias, you have to share your screen.
Oh, sorry. I was so excited here. I saw it on my screen here and you didn't see it. Now you should see it again. Are we fine?
Yeah, we are fine. Okay,
this is what I just said. There's all these different systems where you can do this Floquet engineering. You can download the transparencies later if you want to look it up in more detail. What we use is if you want, is a discrete function of that, where we just have this specific pulses, and we are using pi pulses throughout this work, but just putting pi over 2 and pi pulses for just using them in a special way. The simplest one is this pi pulse, which is rephasing all the spins that you probably all know from your classes on physics on the Bloch sphere and nuclear magnetic resonance. So the way it works here is you take this Hamiltonian, in our case it's an XX Hamiltonian, just flip-flop interaction. This is the natural Hamiltonian. You send in a sequence of pulses in different bases with different timings, and you can actually arrive at a fully controllable XYZ Hamiltonian. And how does that work? The way it works is you use these Floquet cycles here at different times, always pi over 2 pulses with the right timing. And what you actually do, and it's hard to explain that here, and you can look it up if you go to our paper, is you just switch at every time, you you change the Bloch sphere and you let the system evolve in the meantime coherently, and then you switch the Bloch sphere again, and you go and you go and you go. You flip your reference frame several times, and the magic that occurs is if you do that and you stroboscopically then observe it, this system actually can be described by this average Floquet Hamiltonian. And as it turns out, if you do the averaging, and that's worked out here, I spare you the details. If you work it out here through all these different switch bases, then what you find is that at the end you arrive, as I said, to this general XYZ Hamiltonian starting from a simple XX Hamiltonian. And just in the last remaining minutes to show to you what we observed here is we initialize the system in a given state, we let it undergo this evolution, and then we read out what kind of state we have in the magnetization to show that we have this Hamiltonian. And as I showed earlier, what we typically see is also for this XX Hamiltonian, we see this dephasing of the magnetization with time, again, being described by some kind of stretched exponential. But now what we can do is we can turn on this periodic driving, this Floquet engineering, and we can stall the dynamics. And that is what you would actually expect for an XXX Hamiltonian, where all the degrees, all the different magnetization, all the different directions are constants of the motion. It's still not perfect. We understand why it's still not perfect. It has to do with the fact that we have finite pulses. The radio frequency power is not perfect. And it also depends on still having some atoms that are determining the dynamics that are close to each other. In order to avoid that, what we can do is we can let the system evolve under the action of one Hamiltonian for a while. That is already spreading, if you want, spreading already the magnetization along the sample and preparing some interesting but not describable many-body quantum state. And then we turn on our Floquet Hamiltonian engineering, Floquet Hamiltonian, and at this moment, we just stop, the evolution just stops, because the system got into now, no matter which state I am in the beginning, everything will be just an eigenstate of the total Hamiltonian because of the symmetry of the XX, of the XXX. So you can now do, for example, experiments where you tune these different parameters that are entering into this Hamiltonian here, in particular this delta. And this system has a symmetry if delta is 1. It has another symmetry if delta is not equal to 1. And you can then see how by driving the system, there's a non-monotonous changing of the magnetization. Here there's no driving, that would correspond to here delta being 0, here it's 1. And then you go here through this sequence and you go back actually to another value. Here this is delta equals 0, it goes up to 1 and then it goes down again. So it's a non-monotonous evolution that is also then indicating this, this breaking of the symmetry. And what you can also do, and that is very recent here, you can start from an initial state that you just choose, and you can now study all the different magnetization components, and you can now really break symmetry by symmetry. For example, you go from an XXZ Hamiltonian where MX is still observed. You can see we start from a state that has MX and that has MX and MZ components. The MZ component is staying constant in this case, whereas the MX component undergoes, MY component goes some dynamics. And if we now break this symmetry, all three components undergo this relaxation dynamics, except of course MX component, which was 0 anyways right from the beginning. So what I want to show here is that just by doing this Floquet engineering, you can use a many-body Hamiltonian, naturally many-body Hamiltonian, and you can then change it to whatever you want within certain limitations, and you can study this system and its dynamics from a natural system. So that's what we are also currently investigating together with Antoine at the Institut d'Optique. We want to check whether we can even engineer time reverse Hamiltonians. What I mentioned already is there some indications of the fluctuation dissipation theorem beyond equilibrium. Can we see pre-thermalization dynamics? And of course, you would like to map out then phase diagrams for these systems, in particular when they are ordered. Just let me summarize. The Rydberg atoms are really a great platform for implementing spin systems. I mean, you have seen that they are also a great platform for other physics in previous talks. We saw and we found some interesting dynamics that is independent of the microscopic details in this kind of disordered system. And we can now actually engineer the Hamiltonians using this Floquet driving. And if you want to read more details, I refer you to these papers, which I also placed at the additional material that you get from this talk. So this is part of the group here that you can see here on this picture. Some people already left here, like Pound. She went back to Thailand. There's some people that are not on the picture, like Clément and Titus and Andre. This is the theorists that we work together with here at different experiments. Shannon was working with us at an early stage. He's now in Strasbourg, professor, and Adrien, he's now working for Pascal, this quantum startup company, who was a postdoc. And this is my team in China. All right, with this, I would like to finish, and I'm happy to ask any kind of questions. Thank you very much. All right, maybe we just stop sharing here.
I have a quick question. So when you prepare these Rydberg excitations, is there a chance that you also ionize them? By
of course.
photons?
Yeah. I mean, our big enemy is always ionization. Ionization will kill everything. One ion in the sample will have such a strong interaction with all the Rydberg atoms that this nice description in terms of the Hamiltonians, we can completely forget it. But on the timescales that we are having, 10 microseconds maximum, actually most of the experiments we do even at shorter times, we don't see indications of ionization. But that is really something that you have to really worry about. And if we see actually ionization occurring when we wait for longer times, at this moment, we can no longer ignore the mechanical forces on these atoms, and they might even collapse and then undergo penning ionization or things like that.
Okay.
Maybe just a remark on this, additional remark, motion might, I mean, I can't exclude at this level here whether not ionization, but motion is still somehow something that we have to consider in the analysis of these experiments. I mean, you can see that things sometimes fit, sometimes they don't fit so well. So motion is something that one has to consider, and we are still in the process of trying to understand what the role of motion might be in these experiments. But ionization, we feel pretty confident that this can be ignored for these experiments.
Okay. And I guess the way you described it, your experiment also does not depend on the atomic density. I mean, as long as you have sufficiently dense that there will be like...
Yeah, it depends how you look at it. I mean, it depends on the atomic density in the sense that the role of the blockade effect, that means the pair correlation function that we start with in these spins, that depends on the density. And that was the surprise that we had in this glassy dynamics experiment, was that the dynamics didn't depend on that, although there was a strong impact or strong change in the degree of order in the system. Yet we found this universal scaling. So in this sense, we use the density to also play with the transition from a totally disordered system to a system that is already slightly ordered.
Thank you. Yeah.
I guess there is no question in the chat. So anybody else can ask Professor Weidemuller.
Yeah, I had a question. If you can comment on the experiments you were talking about, like I think just mention about the out of time ordered correlators, like are this like post-selected?
Yeah, that is something we want to do next. Yeah, that we want to access these out of time correlators, and what we would need to do for that, and we are currently on the way of doing it, is we would have to we would let the system evolve for a certain time, and then we would slightly perturb the system, and then do measurements. One of the big questions is then this would first lead us to similar experiments as people consider in the spin systems aging. That is one of the things we want to study there. One of the important questions then to consider is how can we access these two-time correlators, because every measurement influences, of course, the many-body state of the system. But there are proposals, and we probably would have to, yeah, we would have to rely on certain tricks to get access to these correlators. It's an interesting goal, but it's also, there's some work that needs to be done. So the first thing we want to study is this aging dynamics. That is the low-hanging fruit. The higher hanging fruit is this out-of-time correlators.
Okay, I guess let us thank Professor Weidemuller for this wonderful talk.
Yeah, great pleasure, and enjoy the rest of the school, and hope to see you soon, all of you, in person in India or elsewhere, in Heidelberg or elsewhere on this planet. Okay.
Thank you.
So have a great remaining school, and enjoy the talk of Johannes, who's next.
Thanks a lot. Thank you.
Thank you.
Thanks.
Bye-bye.
Bye-bye.
So should I
Sadiq.
take
Yeah,
over?
Sadiq, could you
Yeah.
take over? Yeah, so
Yeah.
Sadiq will be chairing the sessions, the rest
Fine.
of the talks, yes.
Right. So, okay, I can see that Johannes has already set up his presentation. So I'll just give a brief introduction to Johannes. So Johannes did his diploma thesis from the University of Mainz, and followed by a PhD from in the group of Anton Zeilinger, and also with Professor Jörg Schmidtmeyer. And subsequent to that, he went to NIST, where he worked with Bill Phillips. And after that, he had a position at the University of Innsbruck, and following which he has been at Ulm, where he is now the professor and head of the Institute of Quantum Matter. And look forward to your talk, Johannes.
Thank you, Sadiq, for the introduction. It's very nice to be here. So I want to tell you today about ultracold chemistry with a molecular ion. And this is barium rubidium plus ion as it collides with ultracold rubidium atoms. These experiments have been carried out at the University of Ulm. But before I get into matter, let me just quickly show you a picture where Ulm is located. It's the southern part of Germany, and it's the birthplace of Albert Einstein. For those who don't know, there's the Danube flowing through Ulm, and we have the highest church steeple in the world. Good, so cold chemistry with ions. So here we have our molecular ion, an atom, and we will see that there's a long range interaction between the two, which goes like 1 over r to the 4. And this will also result in relatively large cross sections. An important process that we will need is the Langevin collision. And one thing that I should point out from the beginning is if you perform chemistry in an ion trap, then because the ion trap potential is so deep, ionic products are normally not lost. And that means this makes it possible that you actually track the evolution of an ion through several reactions. So here's the experimental setup. So we combine trapped ions and trapped ultracold neutral atoms. For the trapped ions, we have an ion, a Paul trap. This is very schematic here, just 2 electrodes. And the Paul trap can trap barium, but all the other ions too, like rubidium, barium, rubidium plus, rubidium 2. We always start out with a barium plus ion, and it's cooled to about 2 millikelvin. Now, then we bring this ion into contact with a cloud of ultracold rubidium atoms. They are at a temperature of about 1 microkelvin, and they are held in a dipole trap, which is just a focused optical laser. And then reactions can take place. So originally you have the barium plus, and you can see it with your eyes or with a camera because it gives off fluorescence. When you irradiate it with a laser beam of 493 nanometers. But once it reacts, it gets dark, of course, it turns dark. That's the signature that the reaction has taken place. And what I will show you later is, although we don't see the ion anymore, we can still prove that it's there, and we can even measure its mass. So let's now talk about a little bit atom-ion interaction in general. Let's say you have an ion, could be barium plus. This has, of course, an electrical field. You have an atom which is neutral, for example, rubidium, and this rubidium now gets, of course, polarized to the electrical field according to its polarizability. And there's an attractive interaction if the rubidium is in a ground state, and this attractive interaction follows this polarization potential, which is essentially just the electrical field times the dipole moment. And if you plug in the E field and the dipole moment, then you see that this actually goes like 1 over r to the 4. So this is this 1 over r potential that we're talking about. And this looks like this. Of course, at short range, it has a repulsive part. And you got to compare this now to the 1 over r to the 6 potential for the van der Waals, which you have between neutral particles. So one of the most important reactions, of course, of atoms and ions is charge exchange. This is what you see here. So let's say you have the barium ion, you have the rubidium, they collide, then the charge, the positive charge, can hop onto the rubidium, making it rubidium plus, and now the barium is neutral. In our case, there's also a release of energy. It's actually a photon that's going to be given off. Now, what is important is that this process only takes place if the two particles really get close to each other, and it has to be smaller than 30 Bohr or so. And that is because the electron has to tunnel or hop from one orbital to the next one, and there has to be a decent overlap. Okay, so such a close encounter of ion and atom, that happens in the so-called Langevin collision. And this is how this works, this Langevin collision. Let's say you have a rubidium atom sitting here, and there is a barium ion coming from the right with a certain kinetic energy. Now here you see this is the impact parameter B. If this impact parameter is very large, then of course the ion will feel a force and will be slightly deflected. But if it's smaller than some critical value, which is BC here, and it's a function of this C4, this polarizability and the kinetic energy, then in a classical picture, the ion will actually spiral onto the atom and they will really hit each other. And so this is the Langevin process. And in this process, of course, then you can have a charge exchange or other chemical reactions, spin flips, and so on. The cross-section for this Langevin process is given simply by pi BC squared. So let's look again at this charge exchange, which you see here. But now we use the picture of the potential energy curves. So here you have the curves. This is the energy. Down here you have the nuclear distance. This is our entrance channel, that what we prepare. We have neutral rubidium and barium plus. And down here, this is the exit channel, where we have rubidium plus and barium. So the charge has changed. This entrance channel has higher energy. And of course, now you have two valence electrons, one sitting on the rubidium, the other one on the barium plus. And the two valence electrons, of course, they can give a total spin of 0. So this is a singlet potential, or total spin of 1, which is triplet potential. So you have these two potential curves here. But you only have one potential curve for the ground state, because the two electrons here, they share the same s orbital of the barium ion. So the spin function has to be antisymmetric. Now, you can have this photon event where you have the charge exchange. A photon is given off, but it turns out that process is relatively rare. You need about 10 to the 4 or 10 to the 5 elastic collisions before one such process happens, and that is because a photon has to be given off. By the way, you could also produce molecules in this way, in the same process. Now, in our experiment, we produce these barium-rubidium molecules but via three-body recombination, which is just much faster in our case because we have decent densities of rubidium atoms. So what happens is that you have the barium ion and two rubidium atoms, they collide. Rubidium and barium combine to form this barium-rubidium plus molecule. And actually the third atom, rubidium, it takes away the binding energy or some part of the binding energy, which actually stabilizes that molecule. Now, in a simple mechanical picture, this process looks like this. You have the rubidium atom, you have the barium ion. Let's say we have an elastic collision between barium and rubidium. The barium would normally then go out again, but right now it's going in. At that point, there's another rubidium flying by, which now pulls a little bit, it tracks the barium, pulls a little bit the barium and slows it down. And at that point, then a bound state can form. Okay. So how fast is now this recombination rate? For this, we have here this rate equation. The rate is given by some rate constant K3, which is given here, times the atomic density squared. If we plug in the atomic density in our experiment, which is like 8 times 10 to the 13 per cubic centimeter, then you see that you have a recombination rate of 7,000 or so per second. And that means there's a production time scale of 150 microseconds. So this means if you have your barium ion, you put it into the atomic cloud, then within 150 microseconds or so, you will have the formation of this molecule. And so now the question is, what state is this molecule actually in, and how deeply bound is it? Now, here's the entrance channel, again, of the two particles, and you have two potential energy curves, and in either one of those, the molecule will be formed. And now there's an interesting and useful rule of thumb that is actually the binding energy of the molecule that will be formed. This will typically be on the order of the collision energy between the two particles. So if you have, as an example, 2 millikelvin barium ion that collides with the ultracold atoms and forms a barium plus molecule, then typically the binding energy of this molecule will be like 2 millikelvin. Okay, so I mean, I think it's not directly clear how this rule of thumb comes about, but I can give it a little bit of a hand-waving explanation. So here you have some potential energy curve. You want to bind, form a bound. Here's the rubidium, here's the barium, and the barium initially has some finite kinetic energy. Now you have to take out that kind of energy in order to form a bound state, and for that you have the second atom which pulls on the ion. But so the interaction energy now between that ion and the rubidium atom has to be of the same scale as the ion kinetic energy that you have. And that kind of sets a typical distance scale. It turns out that the distance typically between atom and ion here and atom and ion there needs to be of similar distance to be efficient. And so the distance scale then sets again the binding energy scale. So in the end, the energy scale of the ionic kinetic energies kind of sets the binding energy scale. So now we have this weakly bound molecule, and it's therefore highly reactive. And so now we want to know what is it doing? What is going to happen to it in all of these atoms? And this is now the case study that I want to talk about. So it's some research that we have done, recently published, and it's a collaboration between the University of Ulm with Jesus Perez Rios from the Fritz Haber Institute, and Jesus will give a talk later today, and also a collaboration with a group of Olivier Dulieu in Paris. So here's again our playground, and just for simplicity, in the following, I will always have the singlet states, the singlet potentials on the left-hand side, and the triplet potentials on the right-hand side. So now we want to ask, so we produce these molecules, but in which of the potentials are they going to be produced, singlet or triplet? And you can make a simple estimate by considering what is the spin state of the initial atoms. So the rubidium atom is in F equal 1, MF equal -1. It's been polarized. And the barium has been laser cooled. It doesn't have a hyperfine structure, so it just has an electron spin, 1/2, but it's unpolarized, so the spin can be plus or minus 1/2. Now, if you assume that essentially there's no spin flips, the two particles are far apart from each other when they form the bound, and you just project, barium or rubidium onto singlet or triplet, then you get that 25% of the particles will be created in the singlet state and 75% will be created in the triplet state. Now, once you have the particles, or there is a particle in the singlet state, as we discussed before, it can radiatively decay into the ground state. But if you have a particle which is in the triplet state, it cannot, because of selection rules, of course, then triplet would have to become singlet. So we want to investigate this a little bit more in detail. And for this, we are now going to look at vibrational bound states, which I have indicated here. And in the following, I will leave out these potential energy curves for simplicity. So here, now we have the vibrational levels for singlet. Here we have the vibrational levels of the triplet. And this V is the vibrational quantum number. So it's negative because we start counting down from the threshold. So V equals -1 is the most weakly bound vibrational level. And then, we go down. Now, what I want to point out is that for a given vibrational level, the energies, the bound state energies of the singlet and triplet levels, they are pretty much similar, pretty much the same. This is a calculation here where you see the vibrational quantum number, and this is the binding energy for each quantum number. Now, in red, this is the singlet potential. In red, and in blue, this is the triplet potential. And you see how close they always are. So we said in the beginning that we have 2 millikelvin temperatures, and that will produce 2 millikelvin or so bound states. So this is about here. So this is typically the molecule that we start out with will have a vibrational quantum number of -4, -5, -6, something like that. This is why I've started here with this. And now, okay, one reason why all these bound states develop so similar, why they are so similar, because these potential energy curves, they have the same long-range behavior. So now these particles, the molecules in the singlet potential, they can radiatively decay, as we said, but it turns out that actually the most weakly bound ones, they take quite a time to decay. And the more deeply you're bound, the faster it goes. And this is given by this very simple equation here. The rate is proportional to the binding energy, binding energy up here, to the power of 0.75. So how does this come about? Let's look at the electric dipole moment that can be calculated for the system. This is down here. You see it's peaked here. But what is important is that there's a fast drop off. So it very quickly goes to 0. And this can also be understood because when you have the transition from up here to down there, effectively, this corresponds to a charge transfer. The electron that has been sitting on the rubidium now goes over to the barium. And as it does so, it actually oscillates back and forth, and this oscillating dipole then emits the photon. Now, if the distance, though, is too large, then the electron, because it cannot do this charge exchange anymore, and this leads to this fast drop-off. So this explains this drop-off. So you can only have transitions here in this narrow region. Now, The next point that we have to understand is that if you have a weakly bound molecule, then a wave function looks kind of like this. This is the distance here between the two particles. There's energy, they have a potential energy curve. And you see, because it's so delocalized, the probability to be at these close internuclear distances is very small. But when you go to more deeply bound states, like here, 500 millikelvin, the wave function kind of gets squished together and you have a much larger amplitude. So this explains now why as you go to more deeply bound states, the decay actually increases so strongly. And this is now plotted here again. You have on the x-axis, you have the binding energy, and this is the radiative lifetime. And you see this nice law, which goes just like e to the power of 0.75. Now, as I said at the beginning, we start out with a 2 millikelvin or so molecule. So we're around here, and that means the lifetime due to radiative decay is about 1 millisecond. That sounds short, but as I will show you in a moment, that's actually pretty long compared to other time scales, as for example, the collisional relaxation. So let's talk about collisional relaxation. So if you have your molecule initially here, and then it collides with an atom, then the atom can give it a kick and actually, bring it to a lower vibrational level. So it relaxes vibrationally, and there's also some energy that will be given off. And once it's here, it can, wait for another collision and then relax down to here and so on. So this is this vibrational relaxation, and it works for the singlet as well as for the triplet. So what are the rates for this process? It turns out that this relaxation cross-section is again essentially given by the Langevin cross-section, which we just discussed before. And if you now calculate the relaxation rate, actually, then the relaxation rate is given here. This is the cross-section times the velocity of the ion. And essentially at that point, the velocity of the ion drops out because it cancels out with the square root of E of C. And so you see that this relaxation rate becomes independent of the collision energy, and it is also independent of the quantum number V. So it's a very simple result. What it means, it doesn't matter where we are, essentially, in this vibrational state, and what the collision in detail looks like, we will have a certain kind of clock how our molecule will be de-excited by vibrational collisions. So how fast is it now? So all we have to do is we have to plug in the density N of our atomic gas, and then we get this relaxation time constant, which is 6 microseconds. So every 6 microseconds, then we will essentially have a relaxation. And now we have to compare this time constant to the time constant for the radiative decay, which was more like on the order of a millisecond. So you see that there will be many collisional relaxations before a radiative relaxation occurs typically. Let's have a look at the evolution in this vibrational relaxation. So for this, we have the vibrational quantum number here. We start out with -5. Down here, you have the number of collisions that the molecule has undergone. And these collisions can now be inelastic, but also elastic. And you see in this example, so this is just a single trajectory calculation, that you have a relaxation by 2 units. Then there's some elastic collisions. It doesn't change the vibrational quantum number. Then it relaxes again, and so on. And you see that either there are relaxations by 1 unit or by 2 units. So on average, you see if you look at the curve here that for every inelastic collision or so, there's an elastic collision. And typically, on average, once you have a relaxation, you lose about 1.4 vibrational quanta. So you see that after 30 or so collisions, you actually have dropped quite a bit in the vibrational quantum number to -18. So initially you had a binding energy of 2 millikelvin. Now you have a binding energy of about 200 millikelvin. At that point, the radiative decay actually will become fast enough, will become dominant. So we have this following picture now that, you know, if you create a singlet molecule, it will relax down until it gets to about this binding energy here, and then it will just shoot down to the ground state. Now, this cannot happen on the triplet side, of course, because, you know, it cannot radiatively decay. So what's happening? So what we don't observe in our experiments, actually, that we have still all the particles in the triplet state. So what must be happening is that there's some spin exchange collisions. And that bring now these particles, these molecules over to the singlet side. So how does that work? So you have here a molecule in the singlet state, it collides with an atom. Now in a close collision, the spin of the barium can now flip, and that can flip the spin of the molecule to now become a triplet. But there's also the other way around. So here you can have a rubidium atom colliding with the barium again, and then you become a singlet. And it turns out when you do the calculation that you can estimate that that the rate for this process follows again a Langevin rate apart from some prefactor. And in our experiments, we have determined this prefactor to be 1/14 for this direction to go from singlet to triplet, and 1/42 to go the other direction. So now we have a more complete picture, yeah, where we say, okay, so the singlets they relax down to here after some time, and the triplets they will then be pumped over to the singlet side, and then they can also relax. Here you see a calculation for the distribution of the vibrational quantum numbers in the ground state now. So this is after we have relaxed to the ground state, and then we will have a broad distribution of particles in different vibrational quantum numbers. They're energetically here kind of in the middle of this potential curve. And you could think, so this stops perhaps there, but of course you can still have perhaps collisions between atoms and these molecules and vibrational relaxation, but you can also have reactions. And so one reaction is, for example, that you have the barium rubidium plus molecule, where now the positive charge sits on the rubidium, and you have a substitution of this barium atom with a rubidium atom. So this is producing then rubidium 2 plus, and the barium just, the neutral barium atom goes away. And then even the rubidium 2 plus, if it's not too deeply bound, can still undergo a reaction where the ion is now replaced by a neutral atom. And so in this way you create rubidium plus. And indeed, yeah, when we look at our reaction products after a run, yeah, with a certain interaction time and so on, we find that we still have a couple of % of barium plus. So these are ions that have not reacted. We have a decent amount of barium rubidium plus molecules, but we also have rubidium 2 plus molecules, and we have quite a number of rubidium plus atoms. So these were all the particles that we expected. But now, how do you actually, you might ask, how do you actually detect those ions? I mean, with barium plus, it's easy, but all the other ones are normally invisible. And so what we use for this is a combination of ion detection and mass filtering. And I will explain that in a moment now. So let's say you have the ion trap, okay? And you have a given ion, a single ion, and it has a certain mass m. Then it has, you know, a certain trap frequency. And if we now modulate with that trap frequency by shaking the ion trap, then we can heat it up and remove the ion from the trap, and that works essentially with 100% efficiency. Now, if the ion has a different mass, it wouldn't be affected, so it would be still in the trap. So if the ion is lost from the trap, then we know its mass. So this is how we can filter out ions with, or the ion with a specific mass. And then we just still have to detect whether the ion is gone or whether it's still there. And so for barium, of course, this is simple. We just look at the fluorescence of the barium. If we shine in 493 laser and some repumper, then it takes a couple of milliseconds and we can take a picture. Actually, it's not quite true if the ion after erection, for example, is very hot. For example, if it has an energy of 0.2 electron volts, then it would oscillate around here in the trap and you wouldn't get a picture. But what we can do then is still several seconds of laser cooling, where we also sweep the laser a little bit, and then we can bring it down, make it cold, and then take a picture. So this way, actually, we can distinguish between a cold barium ion and a hot barium ion. Now, still the question is, how do we detect the other ions like rubidium plus or barium rubidium plus, rubidium 2 plus? And there we have a different scheme where we use actually the ion to inflict atomic losses in an atom cloud. So for this, what we do is first we take the ion and move it out away from the center. We do this by putting some voltage here on some end cap electrode, and that takes time between 20 and 100 microseconds, so we can move it out. Actually, you can also move it back in. So it's a very convenient way to stop and start reactions in this cloud. So once it's out there, we now load a new atom cloud, a rubidium atom cloud, of which we know the atom number quite precisely. And then we re-immerse the ion into the cloud and have it now interact for a long time, about 100 milliseconds or 1 second or so. And since the ion has micro motion, which is driven by the Paul trap, and it has a typical kinetic energy on the millikelvins regime, when it undergoes elastic collisions with the atoms, it will kick out atoms because they are just in a very shallow trap, which is like microkelvin deep. So this way, we lose atoms, and over the time, a good portion of all the atoms will be lost, and then we just have to measure the atom number that is remaining to judge whether there was an atom, whether there was an ion present or not. So again, by combining mass filtering and ion detection, we can measure which to what probability we have here left as an ion. Okay. So there's one more tool that I quickly want to mention. And that is, so far, we've been able to start the reactions and stop them and kind of watching what's happening. But there are more tools. You can also manipulate a little bit what's going on, manipulate these reaction pairs with the help of lasers, for example. So you can divert some reaction flux, I would say, by shining in a laser. For example, here you have the 1064 nanometer laser, and it can grab onto a molecule and then excite this molecule and photo-dissociate that molecule. And in that way, you create here actually a barium plus ion in a specific metastable 5D state. And so if this ion, for example, is then produced in this D state, is actually normally dark, and we can selectively detect it by shining in the 614 laser, and only then it starts radiating. So we can test how much flux we have diverted here. Whatever we have diverted, of course, cannot relax down and so on. But what is interesting also is that the cross-section for this photo-dissociation depends on the binding energy. Very similar to what we discussed before for the radiative decay. So the cross-section grows as the binding energy gets deeper. You can see this also here in this plot. As a function of the binding energy, you see the photodissociation cross-section here in blue. This is the state that we consider right now. And so what you have then, again, is a competition between the relaxation and the photo dissociation. And depending on what power you choose for the laser, you would then essentially wait until the particle gets down to a certain level, and then you dissociate it. So it's a little bit of a tool. Now, with all these tools and different particles that we can detect and so on, we can now probe and understand the evolution of this molecule. And the way to do it is to measure the populations of the different ions. Could be barium plus, could be rubidium plus, could be the molecule. But we do it, of course, as much as possible in a state-resolved manner, so that we can distinguish the ground state molecule from the singlet and the triplet and so on. And we do it as a function of time. And then we compare the measurements to model calculations, into which we feed cross-section rates and so on. And of course, we can use parameters to improve the agreement, to improve the model. And from this, we can then get a detailed understanding of the reaction and collision dynamics. So here, I have two examples of measurements. You see here as a function of time, we measured in blue the cold barium ion and the hot barium ion, how it evolves over time. This is here on the y-axis, you have the probability to observe that particle. The upper one, where we have the 1064 laser on, the lower one, we have it off. So you get different data. And, when you put that into your model, you will also get different calculated results. There are some additional curves here for barium, rubidium plus, rubidium 2 plus, and so on. And you can see what the model predicts. And with our scheme, you can also, at a given time, measure it and compare it to the model. So with this, I essentially want to conclude, to summarize. I've been talking about reactions of a molecular ion. We saw that the 1/r⁴ interaction is important. It gives rise to these Langevin collisions, which dominate very much the reactions. We talked about several relaxation processes like radiative relaxation, collisional relaxation, spin flip collisions, and then also photodissociation. And we talked a little bit about the experimental tools to investigate this, how we prepare the atoms and the ion, the molecule, how we detect these particles, their states, and how we can also manipulate the evolution of the particles. So I hope that you can see that there's still much more to be done and investigated, and this can probably lead to, in the future, to many exciting results. Thanks very much.
So thank you for a lovely talk, and you are perfectly on time. So we have time for a few questions. Right now, the chat is empty. So if you want to start asking a question, just click your mics on. And right now, I will just start by asking a question, since there is nothing while waiting for others. So Johannes, the thing is that when you are talking about the collisional de-excitation of the collisional vibrational de-excitation, we have done this kind of calculations earlier, and we found that there is a kind of an almost equal chance of excitation too, because these are all happening in an adiabatic, in a non-adiabatic situation. So there's an equal chance of de-excitation and excitation. So how is it? How do you address this? Actually, I mean, you seem to be going only one way.
No, in principle, you're right. Yeah, you can go both ways, but it depends on the kinetic energy. Yeah, if you don't have much energy, so you're really at the millikelvin level, then very quickly, when you go to the next more deeply bound states, you will not have enough energy to go the other way. Yeah, so then it's a one-way street. So it depends a little bit of what we're relying on is sympathetic cooling of the ion after it has relaxed, and so it has gained some energy by collisions with ultra-cold atoms. And so when we put this into the equation, these were calculations by Jesus, then you clearly see that from time to time, something like this might happen, but this is rare.
So because the energetics, I mean, as you to kick a molecular vibration higher, it takes less energy than to pull it down. So where does this energy actually go in the, it's taken by the free atom, is it?
Yeah, it's shared between the free atom and the molecule according to the mass ratio between the two. So the molecule does gain some energy, and perhaps, you know, if it now collided with that energy, you know, it could in some rare cases also step up again. But in most of the cases, actually it will normally also collide again with some cold rubidium atom, will be cooled down. And so this essentially, it does not happen, or very rarely, especially if you get more deeply bound, because the molecule, the atoms it collides with, they are so cold. Yeah, so it will not have enough energy to get re-excited.
Right. Are there? Yeah. Thanks, Johannes. Are there further questions?
Yes. Yes, I have one question. Spin exchange reaction and the charge exchange reactions, are they interrelated or are they independent?
Okay, so I mean, there are two different processes, but they can happen, of course. You know, if you have a Langevin collision, you can have a charge exchange, but it doesn't have to occur. But you could have a spin flip, for example, you know. So in that sense, they are independent processes, but they are in a way linked over this process of a Langevin collision. Yeah, so the Langevin collision just makes sure that the particles get close to each other, and then there's some option what they can do. Yeah, whether they you know, exchange charges, or whether spins get flipped, and so on. Yeah.
Right. So actually, we have kind of run out of time for these things, but Johannes is an extremely accessible person, so do write your questions in. And thank you for a lovely talk, Johannes.
Thank you.
Yeah, we should move to our next talk, which is by René Gerritsma. He is at the University of Amsterdam. So I'll give a brief overview of his trajectory. So he was he did his studies from the University of Groningen, and then followed by a PhD from the Van der Waals Zeeman Institute at the University of Amsterdam. Following that, he was in the Institute for Quantum Optics and Quantum Information, which is the Innsbruck Institute, where he was with Rainer Blatt's group. Following that, he moved to University of Mainz, and he is now back to his old alma mater, which is at the University of Amsterdam, the same institute, and he is conducting some phenomenal experiments with ions in ion-atom interactions and other things, actually. So welcome, René. And
thanks.
Yeah.
Yeah, thanks for the invitation. It's very nice to give this talk. So nice to hear some of the other talks by Matthias and Johannes just now. And yeah, so I noticed that everybody had a picture of their hometown. Yeah, so Amsterdam tends to look like this. This is actually a view that was also painted by Monet, but the painting looks quite different. But I didn't have time to look it up anymore. But anyways, this is Amsterdam. Well, let's talk about research actually. So here's what I study. I have just like Johannes actually. I have a trapped ion, and I hold it in a cloud of atoms, And the main difference with what Johannes was talking about is that my atoms are actually not rubidium, but lithium, which means actually that they are fermionic. So, and we will see in my talk that this leads to a few differences. And yeah, let me just get into it. Yeah, so there have been, Johannes was talking a lot about this very nice quantum chemistry results. And yeah, when I started looking into these atoms and ion combinations, I had mostly in mind studying quantum physics of interacting atoms and ions. And in particular, I was intrigued back then, and still am, of the fact that if you take a single ion, it is basically a harmonic oscillator that you can control very well. And the reason is that any ion that we choose, whether it's barium or in our case it's ytterbium, we can usually define a two-level system in it. Yeah, like a qubit. And yeah, that actually means that the trapped ion system combines two of our favorite quantum models, namely the harmonic oscillator and the two-level system. And yeah, this guy has shown that if you now combine this with laser interactions, that you can actually control the internal state and the motion of the ion to kind of arbitrary degree, meaning that you can make any state of motion and spin or qubit alike, and you can also measure those. And yeah, so Dave Wineland got the Nobel Prize actually in 2012, not in 2013. So that's an error in my slide that I notice each time that I show it, but I somehow I always forget to fix it. Okay. Yeah, so now what I have in mind is taking this beautiful quantum system and basically plugging it into another beautiful quantum system, namely degenerate Fermi gas. And if we take two spin components, then this gas of ultracold atoms is a very nice system of its own. Yeah, because we can usually tune the interactions between the particles to be either repulsive or attractive. Now, on the attractive side, you get an ultracold cloud of fermions, and on the repulsive side, you can actually make a Bose-Einstein condensate of molecular atoms. Yeah, so my question is, what happens if I now introduce an ion into this system? And of course, you can think of very many things that you can study. Yeah? So the ion is basically a polaron that goes into a gas of polarizable atoms here. So it has to do, so with the central spin problem, I have a spin system here that I put into a system of other spins. Quantum chaos could occur that we could study. And we could study what happens to the ion as we cross this this point here, going from the BC to the BCS side, whether you get quantum chemistry, etc. Now, today I will not go into all these fancy things because we haven't done them yet. But what we did look at is buffer gas cooling. Yeah? So the question is, if you take the ion and you plug it in, how cold can you get? So I will be obsessed today with this question: how cold can I make this system? Yeah, so let me leave it at this. So yeah, so here are yeah, this is, let's say, the vision of what we would have in the end of what the system would look like. So you could take multiple ions, then you get phonons in this ion crystal, sound waves that are quantized, and they would then couple to the fermionic atoms in the bath. And of course, this looks a little bit like a solid state system, where now the atoms are like the electrons, let's say. And a major question actually is whether we can find Feshbach resonances between atoms and ions. And I had to last minute change my slide because actually today our friends and colleagues in Freiburg put a paper on the archive showing actually pretty convincing Feshbach resonances. So I was, indeed, I have to admit, Johannes, I was also reading this paper a little bit in between your talk. Yeah, so this looks very nice. Okay, So why am I so obsessed with making atoms and ions cold? Well, Johannes also mentioned this already a bit, that the ion is of course trapped in a cold trap. And also, by the way, Sadiq yesterday in his talk was mentioning the micromotion of the ion. So when you take an ion in a cold trap, it's sitting in an oscillating field, which means that that when it collides with the atom, it never quite thermalizes. Yeah. So if you take a cloud of atoms and the ion is interacting with it, then the ion temperature will never become the same as the atom temperature, and it will in general be much higher. And I mean, like really much higher. Yeah. So even at zero temperature, the ions can reach many millikelvins or even tens or hundreds of millikelvin of energy. Now, since this is a time-dependent problem, it's hard, yeah, and people have worked especially on the theory of this quite a lot. Actually, also Matthias, there's a paper by Matthias also here, yeah, and we kind of have our, let's say, our own kind of approach to it, because yeah, what we thought is how can you prevent this and this type of heating mechanism that causes the ion to be so much hotter than the atoms. And actually Marco Cettina, back in 2012, when he was working at MIT, he figured out that the mass ratio between the atoms and the ions is extremely important. Yeah? So he calculated that if you want to go to a regime where both the atoms and ions and their interaction between them behave quantum mechanically, then you can only do so if you take very heavy ions and very light atoms. So based on this, we then started building an experiment that is based on 6 lithium and 171 ytterbium. Yeah? Okay, so that was basically the introduction. Let me now get to how you would actually build such a system. Now, back then I was in Mainz when I started building this experiment. So the first thing I did actually was take the train to Heidelberg, which is not so far away, to find out how people there actually work with lithium. And Selim Joachim, who I think will give a talk tomorrow, was quite helpful in showing me how you should do this. Yeah. So what you see here is a drawing of our experimental setup. So what we have here is a Feymans slower that we the drawing of which we got from Selim. And yeah, here the atoms come out and they get slowed. And then here at my laser pointer, we make a magneto-optical trap. And here you see our ion trap, which is a big chunky ion trap. And then the atoms here are in this mod. And it's actually a mirror mod. Yeah, so this is a mirror. So we just need 4 laser beams to make a cloud of atoms here. Then you see a lot of copper here, and that's for all the coils we need. Yeah? Because we need to, if you want to make lithium cold, you need high magnetic fields to reach the Feshbach resonances. So here you see a picture of the ion crystal that we have. So that's inside this ion trap. Here's a picture of the lithium cloud. Okay, so here's a cross section now. So let me run you through this experimental procedure. Yeah, so here, so we trap some ions. So we photoionize ytterbium atoms. And then we can cool it. So this is the ytterbium level scheme. It's nothing to really worry about. Here you have a picture of these ions. So the ions are here, but the atoms actually, they form here. So here comes the cloud of the beam from the Feymans slower. We make a magneto-optical trap, which looks like this. And then we compress it and do all the kind of the laser cooling trickery, yeah, that you have to figure out. And then, yeah, we get a pretty compressed cloud of atoms that is pretty cold actually, and then we trap it in a magnetic trap. So switch off all the light, and we have a magnetic field 0 that we then transport up to where the ions is. Yeah, and but actually when you do this, let me just go one slide back. Actually, you lose some atoms from the electrodes, so it heats up a bit. So it turns out that we're not cold enough to do evaporative cooling. Sorry, I go in the wrong direction. Yeah, so once the atoms are up, yeah, now you see a cross section of the pole trap looking from the top, then we do another magneto-optical trap. So we compress the atoms again, then we shine in an optical dipole trap through the tips of the pole trap here to trap the atoms here. And we ramp up the field to about 750 Gauss, which is close to the Feshbach resonance, and then the atoms start colliding. And then we evaporatively cool down the atoms in about 2 seconds. Yeah, here you see the power in the dipole trap. Yeah, so we reduce it, and here you see the temperature of the atoms. So it's cold then. Okay, and then the situation we have is as follows. We have one trapped ytterbium ion, and then we have a cloud of lithium atoms below it. So the optical dipole trap is not at the same location as the ion. And then we have piezo mirrors that, you know, a mirror with piezos on it, such that with the voltage we can just slightly tilt them, and then in this way we can transport up this cloud of atoms, and then yeah, and then let it interact with the ion. And then we release the atoms. So we generally don't look at the atoms because we have pretty poor optical access, and there's not a lot to see actually, only that there's a cloud of atoms and some rough numbers. And then we actually look at the ion. So what we do is we want to know how cold the ion is. So what we do for this is we borrow some tricks from the quantum people, you know, the people who want to make quantum computers. And yeah, and their thermometry is used quite a bit, and this is usually how it's done. We drive a transition here. You notice it's a quadrupole transition. We go from S to D, so it's not allowed, this transition. So it's narrow, and then what you know if you're in the close to the Lambdicke regime is that the coupling strength of this transition depends slightly on the number of quanta in the harmonic oscillator of the ion. Yeah, so this is the Lambdicke parameter eta, and this is the number of quanta. And of course, if you have a thermal state of motion, then you have a distribution of n. So yeah, then what you will what you will see is that you will get Rabi flops if you're in a pure state. But if you're in a thermal state, then the Rabi flops will dephase. I will show you this in a moment. There's one thing to worry about in the ytterbium. You have that the D state decays to the F state, which lives for 60 years, and part of it decays back, which means that we will never get full contrast in these Rabi flops because 70% decays back. Okay, but that's a detail. And then we can detect in the end whether the ion is in the S or in the F state. Okay. So this is what it looks like. So there's a lot in this plot. So let me run you through it. So initially the ion is quite hot because it's only Doppler cooled. And actually the Doppler limit is about 500 microkelvin here. And you see that the Rabi flops that we take, yeah, I mean, yeah, they don't look so nice. Huh? And that's because there are many motional states occupied. So these there are many Rabi frequencies, so it dephases. Yeah? And you see then as we keep this ion in the cloud of atoms, then you see that the Rabi flops improve, so it gets colder. And from fitting this, we can obtain the temperature of the ion. Okay. So the ion has micromotion, so temperature is not so easily defined. Yeah, but I'll get back to this in a moment. But you see, it goes from the Doppler limit down to, let's say, 100 microkelvin. Yeah, so we have reduced the energy by a factor of 5. So the black line is a fit. The dotted line here is what you would expect if the ion would be in a time-independent trap. But it's not, so the micromotion still plays a role. So you see that you have some offset here. And then you also see the dashed line, which is based on our theory, including the time dependence of the pole trap. So you see that we're a bit higher than we would expect, and there can be several reasons for this now. Okay, but this is actually the first time that buffer gas cooling has outperformed simple laser cooling, because up until now the ion would always heat up once you put it in a cloud of atoms. So that's quite nice. So what do we get in the end? So on average, you have about 6 quanta of motion, and the secular temperature is about 100 microkelvin. Secular means that I don't take the micromotion into account here. Okay. So after we got these results, we of course try to get colder and colder, and this is the coldest results we got. Now you have to imagine that since the ion is in a time-dependent trap, you have the micromotion, and you actually have to measure the amount of micromotion it has in order to determine the total kinetic energy of the ion. So that's what we did here. There are all kinds of micromotion. I don't really have time to go into this now, but we measured them all, and then we get the total energy of the ion. Actually, we also have an atomic energy. So in this case, the cloud of atoms was 2.3 microkelvin. Then when you add it all up, you can calculate the collision energy between the atom and ion. And it turns out that if you do this, you end up at roughly 1 times the S wave energy. So that means that the collisions between the atoms and ions only have basically a single or perhaps 2 units of angular momentum in them. Yeah, so we're very close to the S wave limit, as people working in cold atoms also have it with collisions between atoms. So now the question is, can we see some quantum effects in the collisions between the atoms and ions? And then to check this, we decided to look at spin exchange. So here you see a picture of the ground state of ytterbium and the ground state of lithium. So what we do is we prepare the ytterbium here in an excited, let's say, spin state. And now the idea is that if it collides with an atom, then most collisions conserve the total spin. Yeah? So if the ion drops down here, then the atoms go up by 1 spin unit. And now we can detect this spin exchange. And you would expect if atoms and ions collide that the rate at which the spin exchange occurs should be independent of the collision energy when we are dealing with the classical system, at least, because they are Langevin collisions. Yeah? Well, I mean, it doesn't have to be quite independent, but we should at least see, once the quantum effects start to occur, we should see a pattern in this spin exchange as a function of the collision energy. So that's what we did, and so in the end we can detect whether a spin exchange has occurred. So we had a look at this, and this is what we measure. So we changed the collision energy of the ion by giving it more or less micromotion. And then you see here the spin exchange, and so we measured this. We were not quite sure what to do with it, so we asked our theory friends, Michał Tomza and Jarek Wiater, to help us understand this data, and they fitted it. And from this we got the scattering lengths between the atoms and ions. Yes, so we got a singlet and a triplet scattering length. Okay, so let me briefly check time. It's also for my benefit because I have to teach afterwards. So I'm sorry, Jesus, that I cannot actually hear your talk, but Okay, let me continue then. So this is based on a fit. Here you see the partial waves, S, P, D, F waves in the collision, and this is our best fit. So you see, we were already pretty sure that they were opposite, the singlet and triplet scattering length, and now we're quite sure that, almost completely sure that the singlet is positive and the triplet is negative. They're both large, so they're on the order of the natural unit of interaction length scale between the atom and the ion. So I see some questions in the chat. So if you cannot wait with the questions, then please say so, because I cannot simultaneously read it.
It's up to you, Rene.
Okay.
Whether you want to take the questions now or you want to leave it for the end.
No, perhaps I'll leave it for the end then. Yeah?
Okay.
Then I will
No
continue. Yeah? Okay. So where are we now? Because I had kind of this dream of having a quantum system of atoms and ions, and so what I once did is I have drawn this kind of phase diagram of the system that I'm looking at. So here on the x-axis you have the ion energy. So we measured roughly 200 microkelvin here in the results I was just showing. And here I have the atom energy. And now you see these kind of lines correspond to the partial wave limits in the collisions between the atoms and ions. Yeah? So you see we're right at the edge of the S wave limit. But that's actually the only thing that is quantum about it, yeah? Because you see the ion motion is not really quantized. I was showing that we had like 6 quanta of motion still in the ion. And also the atoms were actually a classical gas. So we were very far away from, we were like a factor 10 away from the degenerate Fermi gas or the BEC, yeah, that you can actually also make. So in the remainder of the talk, I would like to explore a little bit what you could expect as you go down and how you could get there. And what will be the ultimate limits. Okay. Yeah, so let's focus on this one. Okay. On this side of this phase diagram of the atoms, we are dealing with the BEC of molecules. And one thing we are wondering actually is what will happen when the ion collides with the molecules. So these are Feshbach molecules, which means that they are huge, they're really large molecules, like it can be like 100 nanometer big. So they are, yeah, I think it's fair to say that they are probably a lot bigger than any other molecule that we normally deal with. So this is kind of an interesting regime, because if you change the magnetic field, you can even change the size of these molecules. So we want to understand what happens. So let's have a look. So we did some simulations actually together with Jesus. It's published here. So the next speaker actually. And my PhD student Hendrik did some simulations. Yeah. So now the idea is I have an ion in a hole trap, and it's colliding with a gas of lithium-2 molecules. Now, as a function of B field, since these are Feshbach molecules, I can change the size of these molecules. Yeah, you see this here, that's the B field, and also the binding energy. And here's the size actually. And yeah, what has always intrigued me is that there is a crossover. So you can imagine that there is a typical range of interaction between the atoms and ions, which we always call R star or R4. And it's given by this formula where C4 is the polarizability of the atoms. And yeah, the size of the Feshbach resonance and this range of interactions becomes the same at about 704 Gauss. So what will happen there? So this is how we envision it. Yeah? So you will have an ion, and if you have deeply bound Feshbach molecules, then they are very small. And yeah, so the ion will collide with molecules. But as I change the magnetic field, these molecules get bigger. So there must be some kind of smooth transition from having ions colliding with molecules to ions colliding with atoms. So what happens? So, so we did the simulations. So this is not data. We are actually taking data right now, but I don't dare to show it yet because it's too preliminary. Yeah, so we find that at this point, at this field where you go from where this kind of range of interactions between the atoms and the ions becomes as large as the molecules, we see we should expect a different outcome in the experiment. Yeah. So if the molecules are deeply bound, we see that in the calculations that what should happen is that the ytterbium steals one of the lithium atoms from the other one. Yeah. So you should get a molecular ion. That will probably not live very long, like what Johannes was just showing. He had lifetimes of like milliseconds, so that's what we should also expect. But if the molecule is large, and then the ytterbium will break it up. So you see that the outcome will be that you get ytterbium plus and 2 lithium atoms. So that's something that we are now studying in the lab. Now this is all classical, these simulations, we should expect quantum effects actually to play a role, because the collision energy is on the order of the S-wave limit. But this is a much harder problem to solve theoretically. So we will first look at what we get in the lab. Okay. Now, of course, we want to get cold, right? So we want to go that way. How to do it? Well, what is, I think, instructive is to once look at what collision energy we have reached in the experiments so far. Now, since the ion is much heavier than the atom, actually the collision energy is to a large extent given by the atomic energy, although the ion is much hotter. So this is a bit confusing, but once you get over it, you can get used to it. So if you look here, you see that this cloud of atoms at 2 microkelvin roughly gives you a quarter of the collision energy here. And the other bits are given by the energy of the ion. And most of it here is the so-called secular energy. So that's the number of quanta in the harmonic oscillator. And then there's also the excess micromotion. Okay, so there are 3 directions of motion, y, x, and let's say the axial, that's the long direction of the pole trap. And it turns out this is the biggest chunk along the axis of the pole trap. Why is this? Well, we are dealing with a background heating rate. So the ions actually, because of electric field noise, they slowly heat up, roughly the number you would expect for the type of pole trap that we have. And yeah, this heating effect is competing with the buffer gas cooling. So you end up at a higher temperature. So we think well, there are 2 ways of reducing this. You should get rid of the electric field noise, which will probably be hard, or you have to increase the density of the cloud. Yeah? So that's probably what we would do by adding a laser, such that you get a dimple, and then the density goes up and the buffer gas cooling becomes more efficient. So we expect to get a factor of 2, which of course it's a log scale, so it's not really a lot yet. Yeah. So what else can we do? Well, of course, we can make the atoms colder. We only went to 2 microkelvin. It should be possible to take them like a factor of 10 lower in temperature. Yeah, but then we should evaporate a bit more efficiently, because especially at the end, we're kind of, yeah, I mean, it's not great. I mean, basically, we have such a dilute gas. So I was just doing the calculation after Johannes, well, in Johannes' talk. I think we're a factor like 1,000 to 10,000 less dense than in his cloud of atoms. I think roughly 1,000. Yeah. And so we would actually like to have a denser gas. So of course the advantage is that we don't have to care so much about 3-body effects up until now, but let's see how this will go in the future. Okay, so if we get a colder gas, of course we go to the degenerate Fermi gas. Also the ion should get colder, but there are also limitations here. So we expect perhaps perhaps a factor of 2, perhaps a little bit more. So we go close to this kind of deep quantum regime, yeah, his name I invented myself, but anyways. Okay, there's excess micromotion, which we can probably compensate better. That's errors in the pole trap, production errors mostly. So we think we can probably improve still a little bit, but not really a lot. Perhaps a factor of 2, yeah, so we get close. Then actually, one thing that I was also wondering is that if you take a pole trap, of course, it just has 2 values that operate it. You have a voltage that you put on the electrodes, and then you have a frequency at which you oscillate these frequencies. And I think a relevant question is, could you actually optimize a little bit by choosing the right voltages and frequencies? And so we did some more simulations, because it's easier to simulate than to measure at the data taking a rate that we have. And then my student Eleanor did some simulations, and it turns out, yeah, there should be something to gain here. Yeah, so the data I was showing was taken here, and actually we would expect that if we lower the voltage on the electrodes of the Paul trap, which are given by the Q parameter. That's typical ion trapping lingo here. Yeah, then we can do a little bit better. And also now we had, for the coldest results, we had like 4 quanta of motion. We should go to roughly 1, according to theory. Yeah? So yeah, so that should gain a lot. That actually is interesting because it makes buffer gas cooling competitive now with subdoppler cooling techniques as well. Actually changing the frequency of the Paul trap, so we are using this frequency, so perhaps we can gain a little bit depending on now how much errors we have in the Paul trap, how much micromotion here, excess micromotion. But it seems by lucky coincidence we almost landed on the correct spot. So not much to gain there. Okay, so yeah, yeah, that's my talk. Yeah, so these the final results I was showing were a little bit theoretical. So we're in the lab now, trying to find these lower temperatures and also look at these interactions between the ions and the Feshbach molecules. Yeah, so this is the team. Actually, I want to mention Jesus, who I think will give the next talk, and also Michał Tomza helped us a lot with this, with understanding this system. Okay, so if you have questions, then go ahead.
Right.
And I will read the chat perhaps in the meantime.
Yeah, so thank you very much for this lovely talk. And yeah, we are open for questions. Do people want to start by asking? So we can go in sequence of the chat. Rohit, do you want to start by asking a question?
I have read the question. Now I can also answer this.
Right, fine.
Yeah, we did not put the mod at the same spot as the ion trap because we were afraid that that the lithium atoms will start coating the electrodes of the ion trap, and then the problem is that the lithium, even in vacuum, will start to oxidize slowly, and then it's no longer conducting, and then electrons can sit on it, and these cause electric fields that will push the ion out of the center of the Paul trap, and then you get excess micromotion. Yeah, so we wanted to avoid this. So we wanted to keep the mod away from the ions. Yeah, but I mean, looking back, I guess, I mean, perhaps that has been a mistake because in the end, especially this transport step, taking the atoms up and then recooling them in a second mod, etc. Yeah, this turned out to be actually quite complicated because we have spent like huge amounts of times getting this working. Yeah? So yeah, so the system has become a little bit too complex. So perhaps in the end, I should have done it differently. But of course, my colleagues, and I think also Johannes has this situation, is they usually have a cloud of atoms that is really far away from the ions. Then they prepare a cold sample and then they transport it up. So I decided to go kind of halfway, you know, have a pretty cold sample and then transport it up and then do the final evaporation at the ion. So yeah, I don't know. I think you could argue about this. Yeah. Sorry, I did not mean that ion cooling by collisions has been shown before. I mean, this, of course, I mean, when laser cooling did not exist, I mean, you could only, so I'm answering the next question now. I mean, people have been doing this, of course, since the 60s, right? I mean, doing buffer gas cooling. What I meant was that that the buffer gas cooling in my lab outperformed Doppler cooling. And I think that was a first time, unless you know another example. I mean, I do not. But, you want to perhaps react? Or?
Yeah. Okay, so that's fine. Yeah, thanks for that.
Yeah. No, sorry. For sure. I mean, Hans Demelt was already working on ions colliding with gas of atoms and even doing calculations. But perhaps I phrased it a bit in a clumsy way. Yeah? Then I apologize.
That's fine. Yeah.
What will be the experimental signature of S-wave scattering? Yeah. So in principle, if you look at Langevin collisions, which is the main kind of cooling mechanism between atoms and ions, that means there's a hardcore collision between the atoms and the ions. In principle, the rate of this should be independent of energy, if you're talking about free particles, of course. And in the case of S-wave collisions, this is also the case. It should be independent of the energy of the two particles, but the rate itself will be different. So that's what we were trying to look for in these spin changing collisions that also depend on the Langevin collisions. Now, the better way to do it in the end will be to look at Feshbach resonances. Yeah. So today, if you're into this atom-ion business, then check the archive today. Yeah? There's a beautiful reprint by our friends in Freiburg, where they show Feshbach resonances for the first time. Now, and these you can start to fit, and then once you fit those, then you can assign the resonances to quantum numbers and also to angular momentum quantum numbers in the collisions, and then you can show it's only S-wave. So that will be in the end the real signature. So we only showed in this paper now that there are quantum effects. So you see this wiggly thing in the charge exchange. Okay, that's quantum effects. Let's put it like this. What would you have changed if you would have considered atom and ions of same species? Yeah, so I'm not interested in that, to be honest, because if I use the same species, I have two choices. I can either choose an ion of an alkali atom, yeah, but that doesn't have internal states. I mean, that's like a helium atom, you know. I mean, there's nothing you can basically do with it. It doesn't have a qubit, you know. It's yeah, so that's not really my cup of tea. So I prefer not to do this. The other option would be to have an earth alkali atom, but I think those are very hard to work with. Of course, in Amsterdam, Florian Schreck is working with strontium atoms, but yeah. So, but I'm more of an ion trapper, I guess. So I'm not. Yeah, I don't want to do too complicated atom stuff, to be honest. But yeah, so yeah, but okay, let's put it like this. I mean, we can, of course, we have. I did not show this, but we have also. We can also make Rydberg lithium atoms, which means that we can also ionize them, the lithium atoms. So we could perhaps potentially in the future ones look at lithium plus and lithium, like you, Sadiq, but then. Of course, we have lithium 6, but yeah, I think probably not. I mean, we prefer to trap ions, I guess. So yeah, there's enough to do, I think.
Oh yeah.
So yeah.
So I think we are running out of time.
I mean, I do regret perhaps not having used barium, especially when I see the results today. Yeah, so perhaps barium would have been a better choice for the ion. But anyways, yeah.
So yeah, I think we have run out of time. Thank you very much, Rene, for this lovely talk.
Yes.
And
I apologize that I have to go immediately because I have to teach in 5 minutes. So I wish Jesus good luck with his talk, and then yes, and we'll talk later, Jesus, for sure. Yeah.
Right.
Bye.
Hi, Jesus. So welcome. So I will now. This is the last talk in this particular session, and is given by Jesus Perez Rios. Jesus did his PhD from University of Madrid, Universidad Complutense de Madrid.
It's fine. It's fine.
I'm sorry if I messed up the pronunciation.
That's okay.
But yeah, just my Indian tongue cannot wrap itself around some of these pronunciations. Anyway, sure. Beyond that, he went to École Normale Supérieure, where he did a postdoc, and after that, he was in Purdue with Professor Chris Green and Professor Francis Robichaud. And after that, he actually took up a position at the
Universidad del Turabo, following which he is now at the Fritz Haber Institute, where he has his own program and team, and he's running a whole bunch of theory calculations supporting experiments. Okay, over to you, Jesus.
Yeah, thank you very much for the introduction. Also, I noticed that as we are moving through the meeting, the number of participants is getting down, right? It's funny when you are the last. So then I will try to make it shorter and nicer also because it's getting late for you guys and it's Friday afternoon, right? So you should go and party. Well, that's not good now, right? But anyway, so my talk here, I'm the only theoretician of today, so it's kind of good and also interesting. So my idea is just to present a particular perspective about cold chemistry, maybe a little bit different. And of course, I would like to start saying thanks to the team. Of course, without them, everything will be much more harder. So Shangeli is a PhD student, Marjan Miramadi is a postdoc, and Miruna Kretu is a summer student. Here's the website for group if you are interested in it. So what we're going to talk. So I know that the point of this meeting or this is try to educate, right? To give like an overview. And this is what I'm going to try to do. So what is free body physics? So I'm pretty sure that if you think about free body physics, you will think about the Efimov, right? And all this kind of universality, which is kind of true. If you think about the cold chemistry, you will have all these things like the talks that we have seen by Johannes and also Rene, like all these kind of wonderful reactions and things like that, right? And then there's a third part, which also kind of was covered by the first talk by Matthias about impurity physics, but of course in a different manner and looking at a different perspective. So I believe that all these three things are part of the same physics, and that's what I want to explain today. So let's start. First of all, what is free body physics? Well, the definition is kind of trivial, right? It's part of physics that deals with free body degrees of freedom. And indeed, it's interesting. This is a research that I did. Like, if you go to the APS has a topical group meeting called free body physics. And it's interesting that you read what is the group for, right? What kind of people are part of it. They said that we are an umbrella organization of atomic, molecular, nuclear, particle, and mathematical physicists, as well as quantum chemists who are interested in the dynamics of simple systems. Also, you can read that systems that have few degrees of freedom are kind of classified as a free body physics. So at the end of the day, what you can say is like any chemical reaction is basically a free body process. And indeed, if you're interested, you can publish papers in these kind of journals if you're doing chemistry, because as I say, it is a chemical reaction. And that's the point I want to make today. So the other part of the talk basically is what is about cold chemistry, but this has been also pretty well introduced by Johannes in the second talk today. Basically, the definition is like, well, it's a chemical reaction between 1 Kelvin and 1 millikelvin. Below 1 millikelvin, people call about ultracold, okay? And this is something related with what Rene was saying about going to this wave limit. This is a wonderful review by Roman Krenz that really states what are the benefits of doing cold chemistry. One of the things is like you are going to be sensitive to quantum effects like resonance, and then you can control reactions and things like that. But the most important thing is like you can play with external fields. At these very low temperatures, what happens is the interaction of your system, atoms or molecules with your external fields are kind of the same order of magnitude as the kinetic energy. So then playing with external magnetic or electric fields, you can kind of make the system do whatever you like. So basically the system is dancing to the music that you're playing, which is pretty nice. One particular example about what is cold chemistry example is this kind of wonderful work by the Narvissus group at Weizmann. So the idea here is to observe, they are sensitive to this shaped resonance or orbiting resonance, where basically what happens is like the incoming particle can tunnel through a barrier, and then you can see that resonance on the cross section. This is a very interesting topic. And also you can, of course, sorry, I have to make advertise on my own book, otherwise it's kind of weird, right? So I have written a book about an introduction of cold chemistry, where basically I cover atom, ions, molecules, and Rydbergs, kind of a general perspective of the field. So now let's go to the topic. So I'm going to talk only about two things. I will try to be short, I promise. Okay, it's late, I know. So one is going to talk about single ion in a bath, in ultracold bath, which is related with the talk of Johannes and the talk of René. And the second part is van der Waals molecules. So I'm going to show you that basically the theory behind this part is also related with this one, which is pretty impressive. So let's start with a single ion in an ultracold bath. So one way to look at that is like what most people believe is like you have your ion in your bath, and then you can look at this as a kind of an impurity problem, right? So basically you can use all these many body approaches, which are pretty impressive, and then you can study all these kind of coherences, quasi-particles, and all that business. However, I'm a fluid physicist, so for me this is then transformed into this. It's like the ion can react with the atoms of the bath and can form a new guy. This new guy is a molecular ion, and this is through three-body recombination, as Johannes explained in his talk. However, what is funny is like when an ion collides with two neutrals, can happen two things, right? So you can have a molecular ion plus a neutral, or you can have a neutral molecule plus an ion. So now the question is, which one is the most important one? Well, also it's important to mention that this process, three-body recombination, is only efficient when you have a high density, because you know you need a lot of these guys and that guy to be able to find in the same spot and collide, right? So you do this experiment. These kind of experiments are very low density, this guy will not matter. In order to treat three-body recombination, the first thing that someone has to deal with or has to think about it is about whether we can use a classical treatment or we need a full quantum treatment. The reason why is simple. A quantum treatment for three-body problems is quite complicated. I mean, it's like not complicated to develop or code, it's complicated in terms of computational time. It is a very demanding problem. So then what I have been doing, or what we do in our group, basically, is like think a little bit, just stop and think. And the way how we do it is basically, it's pretty simple. It's like, if we want to analyze any kind of collisional problem, so this guy will have some kind of low-range interaction, like 1 over r to the n, right? In the case of atom ion, 1 over r to the 4th, that Johannes explained in his talk. So for a given collision energy, basically, it's very easy to estimate how many partial waves of this L here, the centrifugal term, you need for your collision, right? In order to convert to the cross-section. And then this is the result when you solve this. So basically, you need to find what is the maxima and see when the maximum is equal to the collision energy, and then you see which L is that. And this is the expression, okay? So then basically, you plug here a collision energy, and will give you how many L's do you need. So you can also use this expression the other way around. You can say, okay, let's assume that with, let's say, 20 partial waves, it's going to be, for me, pretty hard to see different resonance, because I will have so many of these barriers. I will have so many of these orbiting resonance that I mentioned before in Narvis's results, that it's going to be hard to identify them. And basically, all the quantum effects will be washed out. And if we assume that 20 is kind of the threshold, right, between quantum mechanics matter or the system is so messy that we cannot really identify resonance, this is what happened. So here in blue, I have kind of the lower, so the lower limit where this approximation works. So basically where classical mechanics should work. And of course, as you see, most of these neutral alkali, they are, you know, of course, you need to do quantum mechanics, sure. However, and the moment that you charge one of them, the guy goes really down. And indeed, you see that all alkali plus collisions are within the cold chemistry regime. I mean, below 1 Kelvin and 1 millikelvin, between this range, they all can be treated classically. So in principle, when we try to look at the experiments of Johannes' principle, it is, we can show that there are so many partial waves contributing that the problem, there's no point in doing quantum mechanically, because it's hard and also is not useful, maybe, because we are going to have the same physics here. Say that, then what we did is to develop a method, okay? And our method is kind of funny. I would like to explain, because it's some people don't like it, but okay, I like it. So the idea is a very mathematical idea. So the idea is a mapping problem. So when you have n particles in a three-dimensional space, like in our world, of course, I'm not counting the time after 4 dimension, okay? This is non-relativistic business. I have to be specific. So then in principle, you can map this problem, it's just a mathematical transformation, of course, into a single particle problem in a 3n minus 3D space. This is just a mathematical transformation. And now you can say, okay, why you want to complicate your life too much, right? Yeah, I asked that myself the first time, but then I realized why it's worth it. And it's the reason why. For a three-body recombination, basically, if we neglect the center of mass motion, we have 6 degrees of freedom. So, of course, you can try to treat this problem with 2 impact parameters in 3D, and then spend all your time seeing where are the angles, something like that, and then you get crazy. However, there's something more interesting. If you go to a 6-dimensional space, you can map out your rho 1, rho 2, which are the Jacobi vectors, into a 6-dimensional vector. So then you choose your initial conditions in 6-dimensional space. You go to 3D, use of Newton's equation or Hamilton equations in the 3D space, as you usually do, and then you transform back into the 6-dimensional space. And the reason why is because in that case, the cross-section is so simple as this. So basically, the cross-section in a 6-dimensional space looks pretty similar to a typical 2-body cross-section in 3D, where here we have this guy, sigma b5, it's just the angular element. So in principle, we should have here a 2 pi, right? And here, usually we have a b/db because we're in a 3D, but here we have b4db, just because we are in a higher dimensional space. However, this function p is just the opacity. So basically, it's just the probability that the event is happening for a given impact parameter and collision energy. And this is kind of, at least personally, I feel like very clean theory and easy to apply. This is an example about how it looks like, right? Different kind of trajectories, because at the end, what we are doing all day long is just calculating trajectories and looking how many of these trajectories end up in a molecular formation or not. That's it. And these are different examples for different systems at the same collision energy. But also what is nice is, like, for instance, here is like some opacity functions, like what I mentioned before, like the probability as a function of the impact parameter for different collision energies, 10, 50, and 100 millikelvin. And in this case, I'm choosing barium plus rubidium rubidium. And as you can see here, and what you expect, of course, the lower the collision energy, the larger the impact parameter is. As you expect, just because the lower the collision energy, you are more sensitive to the long range of your interaction. And this is what you can see here. This is just a way to show you what we need. So at the end of the day, in order to get the cross sections, once you know what is the probability, you just integrate that with the factor I showed you before, and that's it. Result. Pretty simple. Here is some of the results that Johannes mentioned something about it. So this is one paper that we had with his group. And basically what they observed there is, like, in principle. So indeed, what we can say is, like, we can, I mean, I was impressed, like our results can really explain the experimental data, okay? And that's pretty nice. And in order to be able to really understand and agree with the case tree, something that we had to realize, which it was kind of a very beginning to be hard, is like, it's important to know what is the energy distribution of the ion. And as you guys know, the energy distribution of the ion in a Paul trap is non-Maxwell bottom. So then you have to do a Monte Carlo simulation to get the energy distribution, and then convert that energy distribution with the energy dependent rate to get the thermal average. But of course, that depends on the macro motion for sure. And then in that case, we have this blue line. This blue line is the result of our theoretical calculations, fully ab initio. I mean, no fitting parameter. I mean, we're just using a model potential, which the only thing that you need is the long range, which is just the experimental long range. But the red line is the experimental fitting. And as you see, the trend is pretty similar, it's a small shift. So we are pretty happy with this result. And of course, something that's interesting, like if you're interested in the impurity physics, like, I don't know, what happened with your polaron, what is the lifetime of the polaron, something like that. If you have like a normal rate of 10 to the minus 24 centimeters, centimeters to the 6 divided by second, and you have a density 10 to the 14, I believe, or 10 to the 13 it was. The lifetime is like 10, you have 10 milliseconds minus 1, the rate. So that basically puts some constraints on your lifetime of your impurity. Once the purity, if and only if the impurity is charged. Okay. So this is something that, sorry, I don't know what is going on. Sorry. No, sorry. What it was. Now I have a problem with this guy. Sorry, saying that I have a problem with the keynote. We're opening. Sorry, guys.
No, don't worry. This is the last talk, so we can take a pause and you can fix your problem.
But I like to be on time.
Yeah, sure. But
okay, now it's fixed. I don't know why this guy just. Sorry. I'm really sorry. This I don't like it. Where I have it.
Hello.
Yeah. Now, can you see my screen? Can you guys see my screen?
Jesus?
Yeah.
Yes,
yeah,
I can.
Yes.
Live? Yeah. You can hear me?
Yes, we can hear you.
Okay, perfect. Can you see my screen?
Yes, but it asks you to reopen.
Can you see it?
So you need to click on reopen.
Yeah. Okay. Stop share. Stop share, and then I will do it again. Yeah, that's a good. Sorry. Now should work, right?
Yes.
Now works, right?
Yes, it works.
Thank you for the tip. Sorry for all these technical issues. I'm really sorry. So anyway, what I wanted to say is something like already Johannes said in his talk. So one of the things why it's interesting to have this, or to understand, at least from our perspective, this ion atom three Boyer combination, is like because seriously. Yeah, I know what I can do. Sorry. I'm sorry. I'm going to fix it. This is the first time it happened to me. Just 1 sec. I need to do a trick. I'm just changing the format to PDF, just to see if that helps, because I don't know why my keynote is doing something funny. Again, I'm sorry.
Don't worry about it. I mean, sometimes these things glitch. Yesterday, I glitched out of my own talk. I mean, it was.
Yeah, but I'm sorry. Share screen. So let's see if now finally works. I have so many screens open. Why do I have to? Okay, this one. So now you see the screen, my slides, right?
Right.
So don't worry. I will go to the point what it was. I want to waste your time. So there we go. Yeah. There we go. Can you see it?
Yes.
Okay, cool. So I will make it a little bit smaller. How I can do this smaller? I'm not you. Yeah, like this better, right? Much better. So sorry again, and thank you for your understanding and for your patience. So what I wanted to say is like the reason why it's interesting to know how three-body recombination occurs is like basically it's kind of the very beginning of a bunch of very complex chemical reactions, as Johannes explained, from further dissociation to spin exchange reactions. So a lot of things that it's going on here. And that's the interesting part here. However, since Johannes already did that, I'm not going to talk about that. But what is interesting, as what I was saying before, is like we found like since the 1/r to the 4 potential is much more stronger than 1/r to the 6, it's possible to show that the cross-section basically is dominated by the long-range interaction between the atom and the ion, and basically the atom-atom interaction is just kind of an expectator. And we can prove that the cross-section scales with energy in this way. Of course, these are theoretical results, okay? There's no experimental results. How to say that the points with error bars is just because we are doing a Monte Carlo, okay? So then what is nice is like we can see applying that theory, that threshold, we can even explain results that people could explain until now at different temperatures for different noble gases. So usually people in the 80s did a lot of ion mobility of different like helium plus in helium, krypton in krypton, and things like that. And in green here, you see our results, which agree kind of pretty well with the experimental ones. So then basically what it means is like when an ion interacts with two atoms, at the end, what you have is molecular ions most of the time. So basically the other channel is highly suppressed. And that's what that means that we can prove, or we have some confidence that the cross-section should go like the collision energy in this way. This is of course a classical Sefton law. At some point, when you are getting really, really cold, this should break, okay? Because that doesn't have any quantum behavior on it. Also, what you can do is something that also René explained. It's what we have been interested in, but it's what happened when you change kind of the background or bath to the ion. So we have the same initial state, an ion surrounded by something. But that something now is lithium-2 molecules. And the good thing is like in the experiment of René, since they have felt molecules, basically changing the magnetic field, they can change the binding energy of the molecule. And then we have a new way to, or let's say a new free parameter to explore in order to understand what is the chemistry behind. And what turns out is like it can happen three things. So basically, as René explained, the ion just can have a reaction where you have a molecular ion, you can break the molecule, or you can quench the molecule, right? That's all the things that can happen. So then how we do that? So basically what we did here is a quasi-classical trajectory calculations. This quasi-classical only means like the initial state of a molecule is chosen in a way that agrees with the Bohr-Sommerfeld quantization rule for the potential that you have. So the only ingredients is having the potentials, and something good that we did here, thanks to Henrik, which is a PhD student of René, like we were able to include not only the secular approximation for the potential of the ion, but also we include especially the time dependence on the atom, on the ion, which is pretty nice because usually when you do what I showed you before about three-body combination, we did not include the effects of the trap. So basically we are doing a free field case. However, the good thing of having the time here is we can also see what are the effects of the trap onto the product. So one of the things that you can think is, well, if you have a weakly bound molecular ion, maybe the electric fields of the trap can tear the guy apart, right? Can happen. So in our theory, this is what we can study. And as I say here, this is just to show you the kind of expression. This is how we can control the final state distribution, just in case we're interested in, of the lithium-2 or the molecular ion, whatever we are looking at. And this is the WKB approximation, as I mentioned, within the QCT approach. And at the end of the day, what we can have, after studying what are the two kind of main reactions, is what we call kind of a phase diagram of the charge impurity. So in principle, you start with a charge impurity in a molecular bath. However, under certain conditions, this guy can tune to a different impurity. You can end up with a molecular ion in a molecular bath. And you can see here that playing with the magnetic field and the collision energy, you can choose where you can end up. So basically, we are studying the tunability of our system and also to see how sensitive is the, how to say, when you have a single impurity, how strict is that? Because at some point this guy can react. And this is what we have in this plot. So now we go to the final part of the talk. And it's about the van der Waals molecule. I like this figure a lot about the small Ico climbing because it's impressive. By the way, this is for van der Waals interactions, as you guys know. I like a lot this sentence about what is a van der Waals molecule. I like to introduce a little bit this here because I know that at least during this part of the meeting, we have been listening a lot about atom, ions, and Rydbergs. And van der Waals molecules is something more like, I would say, more chemistry oriented, okay? So these are one of the definitions of van der Waals molecules. Van der Waals molecules are weakly bound complexes or small atoms or molecules held together, not by chemical bonds, but by intermolecular attractions. So basically, the van der Waals molecules is indeed the van der Waals is a new binding mechanism. So indeed, the binding energy of these things are pretty small, like 10-wave numbers. And what's interesting is that, like when you have the two guys in the long range, the binding energy, it's due to the long range interaction, van der Waals interaction that we have seen in previous talks. However, when the guys are getting closer, the electronic clouds between the two atoms start, to repel each other and to interact. And that gives rise to the short range. So at the end of the day, a van der Waals molecule is just, another normal molecule, but usually the minimum of the potential, the given distance, is pretty long range. So you see between 6 Bohr and maybe 12 Bohr. So that's the difference. So compared with the typical covalent ones, which is like 3 Bohr, it's kind of pretty far away. And also the binding energy is pretty different. We're talking about 1 milli-electron volt, even less, while the typical binding energy for a covalent is 1 eV. So some examples of van der Waals molecules is zinc. Zinc is a very nice thing because it's a closed shell, right? So any closed shell with a closed shell, it will give you kind of van der Waals. But the one that we're interested here is rare gas with any atom. What I mean by any atom is like you have like helium with lithium, helium with titanium, helium with anything will end up in a van der Waals molecule. And what we are going to do is to try to understand how that happened. But before that, I would like to show you one of the most important van der Waals molecules, helium-2. This is a world famous molecule. The reason why it's so famous is because it was hard to show that it really exists. It took several years. From the experiments, of course, that's what I mean. And the potential is kind of very weakly bound. And what is interesting, like it only has one bound state. But this bound state has the property that they call a halo state. So basically the wave function is super elongated. And then it has a really interesting quantum nature. As you can see, it can be as large as a DNA, which is pretty impressive. And this is one of the relations or one of the interest on van der Waals molecules, because these things, since they're weakly bound, may have a lot of intriguing quantum behavior. So how we do this? Again, we apply three-Bohr recombination, and this is just a scheme of the different coordinates. The rho 1, rho 2 is the Jacobi coordinates that I talked to you before. And here, basically, what we have is in orange is the helium atoms in this case, and the blue is any kind of atom. We have done some alkali, we are going to show some titanium results, something like that. And this is what can happen in 3 different trajectories. So some of them go to what they call an elastic collision. So basically 3 particles come in, 3 particles go out, nothing happens. Then, of course, we can have molecule formation. And of course, what happens is like the kind of molecule that you form, the binding energy that it has, it changes. And it depends from iteration to iteration. And this is what we look at. The most interesting thing is like we decided to look at a bunch of them. We look at 6 different systems. So we look at helium with lithium, titanium, arsenide, phosphorus, nitrogen, and sodium. And what we notice, as you can see, the potentials are pretty different, right? So in principle, we will expect like a totally different messy results, like nothing can be said about it. However, we saw that all the results behave the same. What it means, like there's always like kind of power law here, and then there is some kind of change of behavior and another power law for all of them. However, at the point that that happens, change. And we realized that the point where this thing change is the dissociation energy of the X-helium interaction. It is expected to be dissociation energy and not binding energy, just because in classical mechanics, as we are doing, we don't have 0-point energy. So then the interesting magnitude is dissociation energy instead of binding energy. But it's something that it was very interesting to us to see. Like we have these 2 different behaviors. And then we will also realize it's like this part over here correlates basically with the long range tail of the interaction. However, this part over here correlates with the short range of the potentials, as I'm going to show you in a different slide. But the most interesting result was this one. It's like when you calculate the thermal average free-Bohr recombination rate for any of the atoms with helium, the order of magnitude is the same. So it is interesting that some of them has been observed, like titanium. So what we think is like, if you can see titanium, basically you can see everything. By the way, sorry, has been observed lithium and titanium. So then basically the message is like almost everything that you put in a buffer gas cell, which is kind of the relevant temperature here. So let's say that you ablate aluminum in helium, you will have aluminum helium. If you ablate, I don't know, anything that you ablate there, or anything that you put there, you are going to have a van der Waals molecules through triple recombination. And that's what really struck us, because we didn't expect that. And as I mentioned before, here we have the final, how to say, explanation about what is short range, what is long range. Here in the top panel, we have the results for when this is for helium-helium titanium triple recombination to form titanium helium. We have here two different potentials. The blue one is when we are using a full ab initio interaction potential for titanium and helium, but the red one is when we are using this Buckingham potential. So basically, it's a potential where you have the same equidistance but a different well depth. And as you can see, this part over here is the same, doesn't change because the long range is the same as we expected. But then the position where the behavior change into a different power law depends on the dissociation energy, as we already expected. And of course, since the short range is different, we see a different power law or a different behavior here. However, in the lower panel, what we are doing is we are taking a potential that is exactly has different equilibrium distance, but the same depth. And then what we see is like the change between the two trends happen at the same point. And they are pretty similar. So basically, it's like, unless your depth is different, you're going to see a change here. And basically, what it means is like this behavior is quasi-universal. What I mean quasi-universal, like, of course, there is a shift here that depends on the system, but the trend with the temperature here and there seems to be general to all kind of ex-helium systems. And just to finalize, as I try to be fast, is like, I hope to convince you that few-body processes play a relevant role in impurity physics. What I mean is like, if you want to understand a many-body character of a system, sometimes it's good to look at the few-body physics first. Not because they are different, no. It's just because we need help from each other. Then a single ion involves into a molecular ion in atomic molecular gas, as we have seen. And then van der Waals molecules emerge as a consequence of triple recombination, which is something that people didn't figure out until now. Hopefully they are convinced. And the last point is like, it seems like anything that you put in a buffer gas source, we can end up in a van der Waals molecule formation. I would like to say thank you guys for this opportunity to organize it, especially to Sourav, Dutta, and also the Radon University, which I'm part of. And you're interested to learn more questions, just you can ask me directly or go to the website or whatever. Feel free. Thank you.
So thank you very much. We have time for questions. So the chat is not yet active. So maybe I will start with a question of my own. So the thing is that you did mention in one of yours, in one of the sections, is that for an ion trap now you are actually looking at the time varying trap potential in order to compute the effect on the trapped ions and the collisions. The thing is that the highest frequency in a trap is at the level of megahertz. And if you just look at the collisional times for these charge neutral kind of collisions, they are typically still short. So how much difference is this actually expected to make?
The difference is not in the collision, it's in the products.
You're saying that the branching ratio into the product channel is going to change?
So what I mean is like here, that's something that indeed one referee asked. Okay, that's why we are looking at.
I was not a referee.
No, I'm not saying that you were the referee. I'm saying that if one of these things that a referee asks something and you start to think and say, oh, it's right. maybe we should look it up, right? So this is that's what I was saying. So basically the point is like we can go here or like here, right? So you have a collision. Here, what you say is totally true, right? The trap here doesn't care about the collision. The problem is when you have this guy over here, the molecular ion, what happened to it is now how this guy reacts with the presence of the trap. So in principle, you will say like, but indeed, I have calculation that show that's not true, but it doesn't matter. So you can think like if the binding energy of this guy is like, let's say 100 microkelvin, it's going to be for you very easy to break it, right? Yeah. In principle, you will think that. And that's what we were impressed in these simulations. When we grew the time, we didn't see that thing happen. So this guy survives on the trap. Of course, classically, okay? This is a classical simulation. That's what I mean by dependence of the trap, not on the initial step. Of course, the initial step, we don't care. But the problem is on the products, how the products get affected. And yeah, that's the thing, something that we are still trying to figure out from the full quantum treatment.
Oh, okay. So yeah, thanks.
Yeah, welcome.
Any further questions?
Is a three-body threshold law that you have shown, is this universal? Does it apply to any three-body systems?
Yeah, in principle, I would say yes, but of course I didn't try with all. So I have tried with all these. So basically the idea is, as long as your energy, your collision energy is smaller than the dissociation energy of your system, this should be true, okay? So the thing is, if you try this with neutrals, of course, you're not going to work because this already will break up some of these van der Waals molecules. So this only works pretty well for ion because, as you know, an helium plus helium interaction is way stronger than 78 Kelvin. That is why this can be applicable, or 300 Kelvin. But in the moment, if you do the same experiment at 10,000 Kelvin, this is not true anymore. I cannot apply that because then also the short range part of the interaction plays a role, and then this breaks.
Okay.
Thank you. Thank you for the question.
Yeah, I actually have another question. This is regarding your van der Waals molecule part, and that is, see, for instance, in the the fact that an ion can produce in a cloud of atoms will produce van der Waals molecules is something which is quite interesting, because the way, for instance, in the 80s, I think there were a whole bunch of experiments with helium in supersonic beams, okay, and that was essentially would form van der Waals clusters, and then they were taken to diffraction to a wire mesh of some kind. I mean, and you were looking at diffraction, and different masses would diffract to different angles, and therefore you could detect what is the level of the van der Waals molecules and clusters. So the thing is that van der Waals molecules and clusters is actually forms in supersonic expansions. Now, is this another completely different kind of a scenario in which
that's a really good point. So indeed, you're totally right, of course. So indeed, the first observations of van der Waals molecules were in supersonic beams, right?
Yeah.
But then there has been some experiments in a buffer gas source. So basically, as you know, in a buffer gas source, you have 4 Kelvin, right, due to the helium. And then people thought three-body combination supposed to be more efficient the lower the energy you have, right? So then they thought, if I have a lot of helium, because you have like a lot, and then I ablate something on it, at some point, I should have three-body recombination and form these van der Waals complexes. And indeed, it has been shown for lithium helium and for titanium helium. Mm-hmm. These are complicated systems to do in a supersonic expansion, because in this supersonic expansion, basically you have something like is seeded or basically the same gas. So if you ablate and then you have supersonic expansion, I think that's going to be hard to observe. And also the beauty of this experiment that they did in the buffer gas cell is like you have a good and easy optical access, and then the spectrum is pretty clean. So they can identify the different raw vibrational states of the complex that they form. So now the question is the same mechanism of formation in a buffer gas than in a beam? That's the question that we need to ask, and we are working on that. Because in a beam, what's interesting is at the very beginning, you are hot and dense, and at the end, you are dilute and cold.
Right.
So at some point, there should be kind of a threshold, right? Going from one side to another. And that's the part we are trying now to investigate, trying to see if this is going beyond buffer gas cells. Because of course, this is only up to 20 Kelvin. And this is kind of pretty cold.
Right, right. So, yeah. Okay, thanks.
Welcome. Any other questions, please?
Yeah, well, I can keep asking, but
yeah, you
monopolize.
Please. Just go ahead and ask. I mean, don't be afraid.
I think we are, completely out of time. Yes, but I will get in touch with you later.
Sure,
and,
sure.
Put some questions to you. Yeah.
Yeah, of course, of course.
So I think we have to call the session to a close because we'll have another session following quickly. And I thank all three speakers in this particular, actually 4 speakers. Matthias Weidemuller was also there, and I adabatically continued as the chairperson. But I would like to thank all the 4 speakers. It was an excellent set of talks, and I wish you all a very happy weekend. And yeah, let's continue with some other talks in the evening.
Thank you, guys.
Yeah. Bye-bye.
Bye.
Thank you.